Yeah. Hi, Dr. Pooja. Can you hear me? You are muted, so
Yes, sir. Good
okay.
evening, sir. I am able to hear you, sir.
Okay, good. Yeah.
Yeah, sir. Sir, should we share your PPT or how come? Uh,
It's like I will share from my end. So
okay, sir. Yes, that would be good.
but you
Uh,
need to give me permission, I think, or there is because it was asking for some kind of
sir,
permission.
we have made you a presenter, sir. I think now you will be able to share it.
Uh when I'm trying to share, it is saying we need permission to share your screen. Okay, let me go there. Wait a second, let me just try it. Hmm. Um, it is showing something like we need permission to share a screen. So have you given me the permission?
Yeah, sir, we have given. Dr. Anu, I would request you to check once the settings.
Okay, let me check with the
Ma'am,
settings.
sir has been given the presenter rights.
Mm-hmm.
Okay.
If possible, one of our
Actually,
teammates can share the
yeah.
slide.
Let me just wait a second. Actually, I'm using basically Mac actually. So sometime
Maybe
uh,
that may be the reason, sir. Yeah.
yeah. So I have changed basically. Yeah, it looks like now screen maybe can screen the. Can you see my screen?
Yes, sir. Now we are able to see. Yes.
Yeah. So there was some issue with the my
Right.
yeah. So let me. Uh, okay. Let me see if I can make it forward also. Okay. Now it is in full screen mode. See if you can.
It is, I think, yes.
Can you see in the full screen mode?
Sir, I think it is coming in this form that it is not in the presentation mode, maybe, because it is coming the next slide is also visible on the. Is it connected to a projector, sir?
Oh, no. It is not connected to projector, but okay, I understand. So maybe I should share the windows, maybe not the screen. So now you see, I'm just trying again. Now,
Yes, sir. Perfectly fine, sir. Yeah.
okay.
Yeah, sir. Can we start, sir, now?
Yeah, sure.
Yeah.
Yeah.
So, Ishika, I would request you to please start the session. Please introduce the sir to the participants.
Good evening, everyone. A warm welcome to the second day of the 6-day ATAL Faculty Development Program on Vacuum Technology in Semiconductor Manufacturing and Packaging, Innovations, Applications and Challenges, organized by the North Cap University, Gurugram. Today we have an incredible start, setting the tone with engaging discussion on the fundamentals of vacuum technology, its historical evolution, and its pivotal role in semiconductor fabrication. Our esteemed speaker, Professor V.V. Rao, provided us with valuable knowledge on how vacuum environments enable precision in processes such as deposition, etching, and packaging, ensuring contamination-free manufacture. The sessions highlighted the significance of pressure regimes, gas behavior in vacuum conditions, system optimization, and the latest advancements driving innovation in semiconductor research and development.
With such a strong foundation laid on day one, we look forward to building on this knowledge today, diving deeper into emerging challenges, technological breakthroughs, and industrial applications of vacuum technology in the semiconductor industry. We encourage all participants to actively engage, ask questions, and make the most of this incredible learning opportunity. As we move forward, today's session promises to delve even deeper into cutting edge innovations, industrial applications, and the challenges associated with vacuum technology in semiconductor manufacturing. We have an exciting lineup of expert speakers who will provide invaluable insights into the evolving landscape of vacuum technology and its critical role in shaping the future of semiconductor research and development. Let's begin day two with enthusiasm, curiosity, and a shared commitment to learning.
As we begin our technical sessions for the second day of this ATAL Faculty Development Program, we now shift our focus to a crucial component of vacuum systems, vacuum pump technologies. Vacuum pumps are the backbone of semiconductor fabrication, enabling precise pressure control, contamination-free environments, and high-efficiency processing required for advanced microelectronics manufacturing. To guide us through this insightful session, we are honored to welcome Professor J.P. Singh, head of the Nanoscale Research Facility, GLAD, and Nano CVD Lab at IIT Delhi. With vast experiences in nanoscale vacuum applications, thin film technology, and advanced material processing, Professor Singh has significantly contributed to research and industrial advancements in vacuum science. Let us welcome Sir to share his valuable insights with us.
Yeah. So, so can you hear me now?
Yeah, sir, we are able to hear.
Okay.
Welcome,
Okay.
sir. It's all yours now. Stage is yours.
Okay. I'm thankful to Dr. Pooja for inviting me and also the organizers. All and thanks for the introduction. So let me start with this session, and it looks very the subject the idea of this like semiconductor research and associated techniques. So I really like this idea of having this kind of a lecture series which is mostly technical, which is normally not actually presented or not like organized. Mainly people are giving more focus towards the like fundamental research or the like technical parts, but the technicality or the uh, systems which are associated with semiconductor industry, which is needed for the development is not that much actually clear actually. So what actually I will do, uh, I thought basically I can just talk on small topic in this like in evaporation, that is thermal evaporation. But I would like to give emphasis basically how actually when we actually really fabricate the devices on small scales, or like when we really make some kind of MOS device or semiconductor devices, and mostly the devices are formed in clean room. So I will discuss about some of the techniques, processing tool, which is thermal evaporation, which is one of the tool which is used for metallization part of the processing unit. So giving more idea about like what is happening, how basically the thermal evaporation works in the clean room. So which is little different from the conventional thermal evaporation unit, which is normally in the lab, like when you go and then deposit some thin films or form some nanostructures. So there you need thermal evaporation or evaporation techniques in general, like which can be sputtering, electron beam deposition, those kind of things. But when we talk about basically the devices or the fab lab, then we need to have these techniques housed inside the clean room. So first of all, actually, first I will just share with you, discuss with you basically what is actually I meant with the clean room. So I just go to the next slide. So you can see here that the when we call a clean room, so normally when we talk about the clean room has a control environment. Then we talk about the environment here, actually, not like it's like clean room, how much clean it is. So what type of contaminations are there. So when we talk about the clean room, so you can see my pointer here, na? Laser pointer.
Yes, sir. We are able to see.
So the clean room has a control environment. So there can be low contamination. So low contamination means the dust part contamination means there can be some dust particle, some airborne particle, chemical vapors, etc. So in clean room we try to keep these numbers pretty small. So I'll discuss more in detail like what we meant by that actually. So means we control the number of particles per cubic feet, depending on the particle size also. So that is like if I talk about if I have a room where we have less than 100 particles in 1 cubic feet, and each particle is actually greater than 0.5 micron, then we call that clean room as class 100 clean room. So normally class 100 clean room is well suited for the device fabrication, where we do a lot of like we use basically the lithography methods like either maskless or photolithography, or we go for electron beam lithography. So all those basically the fabrication tools like this lithography processes are done in class 100 clean room. So normally in the commercial level also the devices are normally made either in class 10 or class 100 clean room. So the class 100 clean room which you are seeing is one of the facility which we have at this nanoscale research facility NRF at IIT Delhi. Then you also see there's a class 1000. So normally the characterization tools, when you talk about the characterization of processing tools, so they are kept in under the class 1000 clean room. So you can also see basically the color that actually answer I will give you. So mostly in class 100 you see the color is little yellow, or here which the light is yellow light, and where actually in this class 1000 clean room you see is like the normal LED lights are there. So I'll discuss why there's a difference in the color also when we talk about class 100 class 1. Like the lightning is light, what kind of lights we are use is also very controlled in case of class 100 or class 10 clean rooms. So let us define basically how we classify the classroom. So clean rooms actually. So we have already discussed that when we talk about clean rooms. So normally class 100 means the particle size must be greater than 0.5 microns. And if they are more than 100 per cubic feet, we call it like class 100. And there are also that ISO equivalent for that. Some people talk about class in terms of like class 100, class 1000. Some researchers talk in terms of ISO. So class 100 is like ISO 5, or class 1000 is more or less like we say class ISO 6 actually. So then just giving you some before going to the little more physics about that, like giving more idea, like so this is the technique. You see the electron beam lithography is there, where we have the fabrication tool. RI and PECVD methods are there, which is processing tools, and electron beam evaporator, like which we are going to discuss today, thermal and electron beam evaporator, which is also kept actually inside the clean room. Then we have another physical vapor deposition, which is sputtering unit, which is there. Then we have certain like semiconductor related things like mask aligners, and those things are equipments are also like oxide formations, plasma etchers, atomic layer deposition also, where you can go for one single monolayer deposition, which is also there, that actually kept inside the clean room. So so why we keep actually our deposition systems inside the clean room, and the reason is there can be many contaminants. Then we have already discussed that there can be different types of contaminants which are present, and we want to keep that number low. So so one of the contaminant, what is the sources of the contaminant when we deposit the our film, or we deposit the nanostructures on the surfaces? One of the source of the contaminant will be the outgassing. You see what we mean by the outgassing? Outgassing means like at any pressure there are certain materials which are coming out actually from like in the gaseous phase. So they are continuous supply of the vapors from the material. It can be liquid, solid, so they are coming out, so we call it like outgassing. Which is, then there are some oil vapors which can also be the source of molecular contaminants. Paints and the alcohol or the ethanol which we normally use in the lab for cleaning, that can also be the source of contaminant. Glues, aromatic substances. So there can be different types of contaminants which can start like giving the, which can act like a sources for molecules which are coming out from the material, because all these things actually matter when we talk about the control environment. So this is, so these are basically the molecular contaminants. Then there can be another type of contaminant which we call it like surface contamination. Like so you see like our that's why when we handle basically the surfaces or substrates, we always use gloves. One of the reason is because there is some oil secretion from our finger. So those oils are very high. So if we talk about like why this is a problem, because oil you see is mostly they got like polar molecules. So what happens actually, they get actually attached with the surfaces. They get very high dipole moment with because of that the van der Waals forces becomes very high, and once they get stick on the surface, it is very difficult to take them out. So that is one of the source of the contamination. That's why we always say always use gloves while you are like handling the samples or substrates. Another is like skin oil, any type of hand cream, face cream, or polish actually. So these all things we normally avoid inside the clean room, because they can be the source of surface contamination. So if even you touch some surfaces by suppose bare hand, and those oils can get attached to the surfaces, then basically the surface can start outgassing. And this outgassing is not like the molecule will come out as in one time. It is like there's a time dependence, so slowly the molecules keep on actually dissolving the gases in the molecular gases actually, which will be coming out from the surfaces over the time. So which is very difficult actually then to figure it out. That's why it's like these contaminations also we would like to avoid. These are the sources. And the third types of the contaminants, which suppose we avoid basically the use of the molecular contaminants or the surface contaminants. But the third types of contaminants which is there is basically the researchers themselves, like the people who are working inside the clean room. So you see like our skins, scales, hair, clothing, lint, these are actually, and you don't believe, but actually in clean room the people are the major source of contaminants, because these when you walk through or you work actually, so there are a lot of like our skin part, from the skin particles are coming out of this hair, clothing, which actually contaminate the surfaces. Then there are some particle shedding materials also, that like the paper, cardboard boxes. These materials also actually contaminate. They can actually contaminate the environment also. And there are some other like abrading actions. If there are some drilling, swing, or sanding is there, or there are bare wood products, all these products actually can contaminate the environment. So you see, that's why it is like inside the clean room, normally the material which we are handling is highly controlled. Like we cannot use the normal our A4 size paper or normal paper. We cannot bring that actually inside the clean room, because they can start shedding the particles, like all the boxes. So that's why in clean room we always have some kind of a delivery system, and where the particle from there actually the material can go in a systematic manner from the clean room to the outside environment. Also, all the materials, including the pen or paper, those also are very much different inside the clean room which we are using. So because the idea is we would like to have reduce the number of particles per cubic feet. That is the point. So if we just talk about basically the relative particle size, like why we are so concerned about basically the contaminants here. So giving you some idea that the size which we are talking about is 0.5 micron here. So 0.5 micron, you can see the small white dot is there, that is 0.5 micron. And the basically the smallest size which a person can see from eyes is something like around like 50 micron. So which is something like 50 micron. Human hair thickness is around like 100 microns, and these are the numbers, you can have some idea. So human hair diameter is about like 100 micron, and the smallest size a person can see by the naked eye is something like 50 micron. So you see, so this blue dot, the circle is there, the black circle is the human hair, and then you compare the size of the dust, size of the particle, which is actually taken as a standard for class 100, that is 0.5 micron, which is actually 100 times smaller than the things which we can see by unaided eye. So that's why we have to be very careful about like when we are working inside the clean room. So when we say it's a clean room, it's really a clean room. Like so. Now just giving you more idea, like we have already, I have shown you some one like slide there. So you have seen, so you see basically just comparing the relative size of common airborne contaminants. So if I just go there, so you see the human hair lies here, something like 100 micron we are talking about. The other numbers you can see, if I just talk about the pollen, actually they are smaller than basically the hair, and they lie between something like around like 10 to 60 microns. So this is the pollens are there, so that those pollen dust particles are there, so that those are there. Then we have you can see the size which you can compare is virus. So virus is actually in the nanometers, and few you can say it ranges from 0.1 micron, something like around 100 nanometer to 200 nanometer. That is the size of the virus. Bacteria size actually ranges from some few microns to tens of microns. That is the size of the bacteria. So you see where we are talking about what kind of like what kind of environment we need when we talk about basically class 100 or class 1000 clean room. So that will give you some more idea about that. So you see this is very interesting slide here. You can see here. So here we have this is a real IC surface. So you can see here, this is the scale bar is around 20 micron, and on that there is one human here. So you can see here, so these are the, even the devices are, the one is only one channel. So you can see the devices are even smaller than that actually. So these are the outer, only you can see the interconnections are there. So even devices are much smaller than that. So if you just, even you, one human here can basically damage basically how many number of devices. So that is giving you some idea. So that's why when we work on the clean room, we have to be very careful about that. And this is the reason actually why we need clean room, a very clean environment, or class 100 or class 10, class 100 or class 1000 maximum kind of things for the device fabrication and processing. Now so we learned basically now what type of sources are there, contaminant sources are there. And basically if I just compare the in among all these sources, like we discussed about molecular contaminants, which are the gases like which are coming out from the chemicals or the paint or maybe some material which are inside. Or then we talk about the surface contaminants, which are the grease or maybe the kind of the oil which or we touch basically the surface because of that. And third was the contaminant, which is basically the sources for the people themselves. So if I compare all these contamination sources, then basically the 75% of the contamination is because of the people who are working inside the clean room. So those are the major source of contamination. And then 15% is because we also need some kind of ventilation. So there is always some backflow. So that also generates some kind of contamination, which is 15%. Then the design of the rooms, sometime, because there are some points which which we cannot actually avoid. So those regions, the desorption is always there. So those also, so room structure can also contaminate, and some of the equipments also, they can also contaminate. So mainly they are actually the people who are the major contamination source for any clean room. Now now this is also very interesting. You see here these numbers which you talk about, something like 1 lakh particles per minute, and each particle is greater than 0.3 micron. So you see, basically it also matters like how you behave inside the clean room. Like if you a person who is stand still he's shedding like a lot of like particles. So you can see it's like 1 lakh particles per minute kind of thing, which is greater than 0.3 micron. If person is like just waving hand, or so you see, if the depending on the activity, is the number of particle counts can go like rapidly. Actually, they can rise rapidly. So that's why basically it is advisable when we are doing in the working inside the clean room, one has to be like one has some idea like because they are the major source of the contaminant. So they how to behave, like they have to restrict their activity towards the experiments only. So these are the some precautions one has to take. Now, so as we learned that the human is the major source of the contaminants. So what happens actually? So when we go inside the clean room in class 100 or or 1000, then we have to cover ourselves. This is the reason, because the person, the people, the researcher himself, they are the major source of the contaminant. So what we do actually, just to cover all the parts of our body. So we have to use the head cover, we have to use the safety glasses, then mask, gloves are there. You can see we have to, in principle, we have to cover each and every part of our body actually, including shoe, and then we have the sticky mat, so that any contaminants still are left can take away. So this, when you see a person is working, you go any clean room, you'll see basically the person is wearing these kind of dress, which is basically because they just want to avoid the contamination. That is the major reason. So and any, like I just told you, in any semiconductor industry or semiconductor fab lab, so this kind of dresses are common, and that the reason is because you would like to avoid the contamination. So you don't want to contaminate your samples. So there's the reason. Now so now I think you get some pretty good idea about the in brief, some pretty good idea about the contamination. What are the contamination, what are the sources, how what is actually the clean room. That part was clear. Now I'll discuss about basically the deposition or evaporation part. So mostly when nowadays actually we talk about the fabrication of the nanostructures actually. So nanostructure fabrication using there are many, because when we go for the devices also, like we form the devices in the nanoscale form only, then there are two different approaches for those nanostructure. One is the top down, another is the bottom up approach. So top down, I think top down approach normally we use in the semiconductor fab lab. That is, there are some examples for that. So I'll take only one or two examples for that. And there are bottom up approach only. So top down approach means you started with the bulk material and then you chop down to the smaller level to make to form basically the device on that scale. So if I talk about the what are the top down approach, so one of the conventional method which is used in the semiconductor industry is the lithography process. So how do we use that? So in the lithography process, what is done actually, we use the substrate, and then we put a material which is known as resist, actually photoresist, and we use it like we can maybe you say that by spin coating, we just coat that material on top of the substrate. Then we use some kind of mask to basically basically define the region, to make a pattern. Then finally we use some kind of a lithography techniques. So these the lithography in the those like the radiation which you use actually gives the name of the type of the lithography. Like if we are using the visible or UV light, then we call it like visible photolithography, means it is used by the light photons only. We call it like UV lithography if we are talking about the high energy photons that under in the UV region. Or if I'm talking about like X-rays, you far like then we can X-ray lithography or electron beam lithography, means it means we are using the electrons instead of the photons actually. Then we call it electron beam lithography. There can be ion lithography also. So what is basically the heart of this technique? The heart of this technique is the resist material. Resist is basically a polymer, or sometimes it can be a metal oxides also. And the idea is that these materials change they undergo some chemical change when they are irradiated. Irradiated means suppose you use a polymer and you irradiate with the UV light, then one of the idea will be like the material becomes like it is now becomes more soluble compared to the area which is unexposed actually. So means so this type of material where like the irradiated area becomes more soluble compared to the unexposed material, we call them the positive resist. Or in case of if the irradiated area becomes insoluble, then we call them negative resist. So like one of the heavily used material is like SU8 actually, which is this standard name is there. So which is actually basically we use for UV lithography also. So the reason actually why they become less soluble like this SU8 in case of which is negative resist, because we use like there is like when the light photon actually falls on them, so the polymer start basically absorbing those photons, and they basically cross link to each other, so they becomes hardened actually kind of thing. So when you actually start etching those materials, they will resist that and becomes less soluble. And you have to be very careful, like each polymer when you use like SU8, you cannot use any type of basically light to make them harden. So they have in their spectrum some particular absorption maxima. So normally we use that maxima only to use this material for photoresist actually. So here you can see this picture. I'm just showing you the pictorial form of the lithography process. We have the substrate, you have resist coated on by spin coating, then we put our mask. This mask can be the hard mask also. It can be made up of different material. Sometimes we use the steel mask also, which is having some opening. So this opening, so the mask fabrication is a different process. I'm not going to discuss that, but this separation can ranges from few microns to hundreds of microns also. And so this like these are separations. So where you have mask is hard mask. When you shine the radiation, suppose we shine UV light, so this area which is unexposed, where the mask is not there actually, it's the open area, this material will get basically hardened compared to the area region which is below the mask. So when you like when I do the etching, chemical etching for the particular resist, then actually these materials you can etch out. Then when you remove your mask, you get a impression there. So this like you can get basically the pattern formation there. So this is the way how the lithography works. So now just in brief, just giving the idea. So this is the top down approach. Another idea like which is very recently, like not very recently, like something like 20 years back actually that came into the market, that the idea is nano imprint. So you see in this case the problem is the diffraction limit, because if you have the light which falls on the resist, you see basically the light because if this is a few microns, you see where you know that if the wavelength is of the order of the opening or basically the slit size, then there is a diffraction is there. So because of that diffraction, basically the walls are never perfectly vertical. So you get basically some light which is like getting diffracted from here and goes basically inside this region also. So actually in principle when we need a vertical wall formation, but when we are diffraction limited, So if you go for the smaller scale, smaller sizes, we never get the vertical walls. So we get some kind of a V shape kind of walls actually. So that is one of the reason. And also, so this is the technique where you require multiple steps. So now there is a technique which actually which was actually introduced like I think 2 decades away, and that was basically the nano imprint technology, where there was no radiation, and we just use a mold or stamp rather and then rather modifying this chemical structure with the radiation, we just do basically the mechanical pressing only. So means like I'm just giving you the idea here. So here we put the resist over top of, we coat the resist, a particular resist on the substrate, then we use our stamp or mold, and then we basically press it. So it makes an impression there, and then you can form basically your you can form the pattern which is without using any radiation. So this is one advantage, but the problem is actually this technique, when was it was introduced, it was only able to give you basically the nanostructures of patterning over some polymer films only. But recently there are some reports in which even can go for the hard materials only. So this is the nano imprint technology. Now today what we are going to discuss more about the bottom up processes. So which I just give you examples of top down. So you get the idea, like in top down approach we have two different like we have many techniques. I have not discussed, like there are techniques like focused ion beam and those things are there, but we have not discussed here. But there are a couple of techniques which is top down approach. In semiconductor we are basically using this lithography heavily, and also that's a nano imprint also we are using. Now in the bottom up approach, what is happening there, actually we start building the material from individual atoms or molecules. Like instead of you have the starting material was kind of a big bulk material, you chop down to the small scale. Here we start basically fabricating the material starting from the atoms and molecules. So what is the idea actually? So mostly in the bottom up processes is and mostly there are different techniques also. So one of the techniques, like, so these processes are done under very highly controlled environment. So because you want to control basically the number of molecules and they should actually interact with each other. Also you want to basically you want to avoid the contamination. So there, and we want to limit basically the growth. So there are many methods. So one of the idea is like one can use the basically via the chemical reaction. Like I start with the bottom up processes. One can use the liquid phase also. There can, or in the gas phase also, the reactant gases can interact and they can form the product. So that is there, but I am not going to discuss the chemical processes. There are many methods I have already listed here. You can see the chemical vapor deposition, plasma assisted. There can be molecular beam epoxy also, but so the simplest one is the physical vapor deposition techniques, which we are going to discuss. So so in the physical vapor deposition, what is happening? So in physical vapor deposition is basically we start with the solid material. Like we start with the solid material, and that actually we transform into the gaseous phase by some physical process. Now that actually gives the name the physical vapor deposition. So if I talk about the, now this material is like, so we start point is like we have to convert the material from solid state into the gaseous phase. So the material is then, because now it is in the gaseous phase or vapor phase, then it is cooled and redeposited on a substrate with either with reaction of some gases, or we can have maybe either we use the room temperature or you put like some low temperature. Your substrate can be on low temperature. So the idea is we have to cool these vapors over the substrate, and so they actually form. So your film, either I talk about films or nanostructure, though they are getting formed atom by atom. So that is the idea. So in this case, in PVD conversion processes, like now we need to convert the material, solid state material, into the gaseous phase. So this conversion processes can be are basically in physical evaporation, which we are using, can be thermal evaporations also. That is, I can use the resistive heating. Means I'll show you the image also. We can just pass some high current over some material, which I will show you the image later on, that we use some, so you pass very high current. So in the over the source material, and then material can evaporate. Material can either evaporate or it can sublimate. So that's the idea is there. So this is the method is known as resistive heating, means we use very high current. The current order is normally of the order of like 300 to 400 amperes, more than 200 ampere, and then this current is passed through very highly resistive materials. So that actually the joule heating is very high actually. So we use that idea, joule heating, and then we heat the material, melt it, or we can also sublimate it. Material gets sublimated and it gets start evaporating. Another idea is basically the electron beam heating. So you see in resistive heating, I'll show you the maybe later on the images also. So we pass very high current. In electron beam heating, what we are doing, what we are using, the idea of heating is different here. Either instead of passing the high current, we basically use very highly focused electron beam, which is and we that beam, electron beam, very high energetic electron beam is getting focused, and that beam get falls on the substrate only, or your material, not substrate, or your target material actually, which you want to basically we want to convert into the vapor phase. So and then we start basically rastering this electron beam over the surface slowly, so that actually the material can start melting, or the material can convert into the vapor phase. So this electron beam heating is also one of the idea. Now see the thermal evaporation. The evaporation can be done in many ways. So one is resistive heating, electron beam heating, or we can use, instead of the electron beam or the current, we can also use the laser. Like the laser is like we can use pulse laser, where we can use the very photons, like high energy photons concentrated to some small spots, and that can power, the laser power can also ablate the material. So laser ablation is one of the technique. Normally the name is pulse laser deposition. So this is the another technique, which is also physical vapor deposition. Another is basically the sputtering, which is also very common. Sputtering means we use, I'll discuss that also. We use some kind of the plasma, gas plasma, and which actually removes the target material by bombardment on the target material. Like if I want to deposit gold, then we need some plasma. So those plasma ions will actually bombard over this gold material, and the gold will get finally deposited. So now we'll see like what is the technique and how this works. So let us discuss about the magnetron sputtering here. So magnetron sputtering, which is used in the industries, like here we have two electrodes. So you can think of like I have a substrate here, you see. So it is negatively, we have a substrate here, and this is the target. So the target is actually given the positive, and the substrate is giving the negative voltage. So you can see it acts like a cathode here. The substrate is act like a cathode. I can think of, if suppose if I have some ITO, I want to deposit ITO, indium tin oxide, which is a transparent metal oxides, and normally is very useful for device fabrication. We would like to have the ITO. So this ITO is acting like a target. Then what we do actually, we create some kind of vacuum here, so that we can increase the mean free path. I'll discuss that also. So and then we insert the inside the chamber, we insert some kind of gas, like argon gas, which most of the time argon actually, and we want to make a plasma of argon. So we introduce some argon inside, and then we apply very high voltage between the target and the substrate. The voltage can be up to normally of the order of few kilovolts. And then what happens actually, there will always be some kind of initial like charge particle, so that those particles can get accelerated because of the potential difference between the target and substrate. So they can actually hit the gas ion, which are the argon, and then argon can be converted from argon to maybe argon plus. So those argon ions can actually now start like moving. So they get accelerated. They get accelerated towards basically the material. And what happens actually, So these actually, so they can take out these ions can take out the target material actually. So they can lodge on the target material and they can actually knock off the target atoms from the target, and then finally this when they came out from the target atom came out from the material, they get deposited on the substrate. So over the time actually that there will be a film which will get formed on the substrate. So the idea is very simple here, but there are many variations. What I discussed with you is the DC magnetron. So now people also talk about the RF source also. They use the RF source, so that actually there's another idea, like we call it like RF magnetron sputtering also. And also they use like the magnets also, which are magnets are over the target surface. And the reason why the magnets are there is this, because if you have the magnet, then basically we can increase the path length of this your like the electrons or the particles which are actually moving. So those path length can be increased, and so the number of ions we can increase. So that is like we can that's the idea, because more the number of sputtering ions over the target, more the number of target atom which will get knocked out by these atoms. So these ions actually. So this is the reason, like one of the reason like why people are using the magnetron sputtering is that the deposition rate in the case of magnetron sputtering is pretty high. So it goes like something like 1 micrometer per minute, whereas actually in the normal deposition, when we talk about the normal like either e-beam deposition or thermal deposition, we talk about basically something like few angstroms per minute. So you can get the idea, like few angstrom per minute to 1 micrometer per minute is a very big change here. So also you see mostly in the sputtering systems, these targets are actually rotating, and the idea is to have the uniform basically deposition, because so that there should not be like some kind of hole formation there, and so that uniformly the target will get sputtered out from the plasma, and it can deposited on the substrate. So this is the just kind of giving some idea like what kind of thing is there. Then in the sputtering there can be multiple sources, multiple targets also there. So one can also think of like co-deposition in the magnetron sputtering also. You can deposit more than one material in the single chamber. Now so that was basically the idea about the sputtering. Now we move to the physical vapor deposition here. So physical deposition, as we have discussed, that is the process where we transform the target material into vapor using some kind of physical means. So physical means, like we have already discussed, that there can be the means can be like either providing some high kinetic energy by knocking off the target atom, that is by basically in sputtering process, or you provide high current like in thermal deposition, or we use the concentrated electron beam like in case of electron beam deposition, or in like use basically some kind of a laser like laser light, which we call like pulse laser deposition. So the one of the requirement of any physical vapor deposition is that the starting material has to be very high purity material. So this one one has to be very careful while you are using that actually. So the material has to be very pure. Also basically the cleanness is also very important. So normally we do not we do not use the same kind of a boat or same kind of hut which we use, the crucible which we will use only for one type of material. We do not interchange, because otherwise there will be some contamination. So now this technique, normally the physical vapor deposition is normally used for metals actually, but it can also be used for the dielectric. But mostly for metals it is very useful technique, and in semiconductor for metallization process actually normally we use physical vapor deposition. Now one of the advantage of this technique is that it does not involve any kind of chemical reaction. So but there are some techniques like reactive sputtering, reactive ion sputtering or something, where they use some chemical reactions also, but normally the chemical reactions are avoided here. Now I'll give you some idea, like when we evaporate, like when you do the thermal deposition versus the sputtering actually. So what are the things? Because you see when we want to basically deposit some surfaces, some pattern here. This is the pattern, and I want to have some deposition. So this is my source. So you see the vapor flux are coming like perpendicular to the substrate, which is like in the direction of the substrate normal. The vapor flux is landing actually on the substrate. Then what happens actually in case of the thermal vapor deposition? What happens? We always have the problem here, and the problem is because the coverage is you see we always get some kind of a spotty sidewall or non-continuous film formation here, because see this is like, if this is very sharp boundary, the this side will not get actually deposited. So this is one of the advantage. Sometimes it is disadvantage also. You won't get a continuous film. So if I am just talking about some kind of a contact actually, so in this process there is a chance that you will get basically high resistance here. This because there might not be any deposition actually on the sidewall. Whereas actually in case of sputtering, because sputtering, the point is that the sputtering get actually the better actually step coverage, and the reason is because it use the wider angular distribution. In sputtering, the ions are coming from all the direction, hitting the target surface, and it transfer the momentum, and just to conserve the momentum, basically the molecules are also coming out in the different directions. And also these molecules which are coming out, the atoms which are coming out from the target, they also got some high kinetic energy. So because of that high kinetic energy, the surface diffusion is also high in case of sputtering. So that's why this is the one of the thing, like when you use basically the sputtering technique instead of the normal thermal evaporation, so normally we end up with the continuous film formation. So we do not have suffer with this kind of idea, like a problem like the spotty sidewall we call, or like it's not like coated. The sidewalls are not coated with the film. So that is not there. So this is one of the advantage of sputtering over the evaporation. Now going to the more like fundamental things, like why, because you see in all the depositions normally we do inside the high vacuum actually, or ultra high vacuum normally. And normally high vacuum is sufficient, like unless you really want you want very small contaminations, or very you talk about the monolayer formations, then we talk about we go to very high small high vacuum, ultra high vacuum kind of thing. But normally what we meant by I think you have already undergone the courses, some courses, basic courses on vacuum, so I won't go in that detail, but giving you some idea, like the mean free path. You understand the mean free path? The meaning is that this is basically the free path, like how much time the the ions of vapor atom is free, but it is not under any external force. So it is like particle is moving without feeling any force, and it is free to move only when it reaches its when it actually encounters the another atom, and then it got scattered out from there. So between two consecutive scattering, what is the path? And in that period we can think like the particle is free of any external force. The force is not there, so it is free. It's like it is moving in the straight line. So you see, if I'm just talking about basically that path, so if I talk about the atmospheric pressure, 1 atmosphere, which is close to 760 torr, then basically this distance comes out to be 40 nanometer. One can calculate. So that math you can see here is not very difficult to calculate, but one can calculate that numbers comes out to be 40 nanometer, which is much smaller, which is really smaller than the most chip features. Normally we talk about the 100 nanometer, 200 nanometer. So that is the scale. So just giving the idea actually. And if I am like something like 100 times, like 1000 times less actually pressure, 1000 times less pressure, which is we call it like the rough vacuum, something like low vacuum, then the size actually becomes 40 micrometer, which is now it becomes much larger than chip fusion. And if you go for basically the high vacuum, where we talk about some 7.6 microtorr, this kind of range, then basically this mean free path comes out to be 4 meter. So what is the meaning? You see, normally the deposition chamber which we normally use is of the order of like something like half a meter or so, or less than that. So 4 meter is pretty big distance. So what it means actually, it means that In case of if I'm just doing the deposition, it is basically the line of sight deposition, means the particle will leave the source and it will reach basically your the substrate without hitting. The chances of hitting the gas molecules will be very less, because the mean free path, because the distance between two consecutive scattering is now around 4 meters. So most of the time what happens, it will either, if your source is little away, it will either hit the substrate, or it will hit basically your chamber. That's why this is very important when we use the chamber. Normally when we use the chamber for one type of material, in the industrial purpose, we do not use it for any other type of material, because this chamber actually wall actually get coated with this kind of material, this like your source material most of the time, and these materials can later on get contaminated, if you use some other type of material that can contaminate your like your the substrate. So so because of this high mean free path, which comes out to be 4 meter, like I'm just giving the example here, and the molecules actually evaporated materials will travel in the straight line toward the vapor, which is line of sight. So it means in case of deposition, physical vapor deposition, this is it's like very highly directional actually. Now this is just giving you the idea, basically, if the different gases, if you have different gases there, like the like their pressure, and this just giving the idea like how their mean free path changes. So now I just want to discuss with you another thing, basically is basically the formation of, because now we understand the mean free path. Now now the material is getting deposited, it is direct deposition. Now this material, we can assume that I have the enough vacuum. Suppose if I have a vacuum of -6 millibar, so it means that so the mean free path is like something like, you see something more than a meter, you say tens of meter or hundreds of meter something. So tens of meters is like very large kind of a mean free path. So it takes, like there will be like 3.3, like around 0.3 monolayer will form in 1 second. So what is the meaning of monolayer? What is the meaning of monolayer? Monolayer means excuse me, monolayer means like you want to deposit, you want to cover the whole surface. Like suppose if I want to I want to deposit one atom thick layer of the material uh, over the complete surface, then we call it monolayer. So giving you some idea like how many number of, if I talk about the atmosphere, so there are around 10 to the power 19 molecules per centimeter cube. So if you see per second, there is something like 10 to the power 15 molecules which are hitting the surface in every second. Like you can think of that number, I'm just giving you 10 to the power 15 molecules are actually hitting per second that area. And there are on the surface, you see the surface, how many number of atoms are there in general? Typical number is around 10 to the power 15. So there are 10 to the power 15 atoms are there per centimeter cube, per centimeter square actually. So that actually makes one monolayer. So it means that if I want to form a monolayer, so if this table you see, it's a very interesting table. If my chamber pressure is 10 to the power -4, then it takes only 0.02 seconds to form a single monolayer. If I go for 10 to the power -5, normally we work here like normal lab vacuums are 10 to the power -6, which is easily you can get that. So it just takes only 2 seconds to form one monolayer. So it's like these numbers are like just typical numbers only, not like exact actually. So it takes one monolayer, means like you want to deposit, so it takes only 2 seconds. So 2 seconds actually get, so you see I'm just talking about the background gases, means because when we have when you have the substrate there, it is not basically the material which we are evaporating and they are getting deposited on the substrate, but there are some background gas also. Background gas means like if I talk about the 10 to the power -6, there are still oxygen, nitrogen, oxygen, and the water vapors. They are already there, and there can be some contaminant gases also. Those can also get deposited on your material. So it takes only 2 seconds. So but if I keep my vacuum to very small pressure, if I go to ultra vacuum, which is 10 to the power -9 torr, then you see it takes for one monolayer formation, it takes 35 minutes. So means if I can quickly get the deposition under the ultra high vacuum, then I can make sure that my film is contaminant free actually. So this these numbers are very useful when you really want to deposit a contaminant free thin films. Now another interesting fact actually in there in the case of evaporation things is basically the arrival rate, because you see now we have discussed that the mean free path is very high. So you see, if I'm just talking about 10 to the minus 6, the mean free path can be 50 meter, can be more than that, actually less, like this the order only, don't go by the number, it's just the typical order. So you see, it means now the arrival rate, what is the arrival rate? Arrival rate gives you the idea, like it is the ratio of the molecule, the vapors which we want to deposit at 1 nanometer per second. This is just giving the standardization. This is just for the standardization term actually. So if I have a 1 nanometer per second deposition rate, so the ratio of vapors which arrives actually on the target, on the substrate, to the molecular impact of the residual gases, because when you are depositing at that time, there might be some background or residual gases which are also there, and they are also, because they are also in continuous motion because of the temperature, room temperature, they are moving actually. So they also get deposited. So so there may be a chance that basically your molecule which is actually getting deposited on the substrate, they can also hit the gas molecule. So means if I have the arrival ratio 1, that means the number of film molecules hitting the surface per second is the same as the number of gas molecules. Means the number of gas molecules which are hitting and the number of the film molecules or which you want to deposit, their number is same. So that is basically arrival ratio 1. So we don't want that. We want basically more our the number of the molecules which we want to deposit, their number should be much higher. So actually we would like to have a larger number of arrival ratio. So see, this you can obtain only at very high vacuum. So that's why we have this vacuum in the clean room, we always get deposit basically under the ultra high vacuum. So if I have the ultra high vacuum, it ensures that my arrival ratio is like 10,000. So one atom, we have 10,000 atoms of basically our depositing material. So which ensure that we really get contaminant free film. So that is very important. Now here you see I'm just talking more in terms of the vapor pressure. What is vapor pressure here? So we are depositing the materials, we get some vapor pressure. So then see what is the physical meaning of vapor pressure. So vapor pressure is the pressure at which basically the vapor is in equilibrium with solid or liquid. I'm not talking about basically I'm talking about now vacuum system inside the chamber. So you have vacuum. So there may be, or even the atmospheric condition also. So molecules are getting away from the surface. They are so there is always some kind of a equilibrium between the vapors which are going out and the vapors which are coming back to the material. So there is always some kind of equilibrium. So vapor pressure is basically, when you talk about the vapor pressure, it is that pressure at the equilibrium actually. It's a pressure at the equilibrium only. So when basically our operating pressure is below this value, then the surface evaporation will take place. Means if my vapor pressure means if my operating pressure, I'm doing inside the vacuum, and so in that case basically the surface evaporation will take place. Means there will be more number of molecules which will be dissolving actually. And if my operating pressure is not actually above this thing, then we get basically the condensation. So the vapor just the reverse process actually. So see basically so why this is important. So I'm just showing you the pressure versus temperature graph here. So basically you can see we can determine, I'm just not going in detail of this equation, but you can get basically the vapor pressure here depends on the temperature actually. So you see the materials are having the different vapor pressure at different temperature. So when we are quoting the vapor pressure, we have to quote basically what temperature we are talking about. So for example here I'm just showing you basically the vapor pressure versus temperature of different elements here. So you can see here the silicon is having this is the line for the silicon. which is varying from here. So in most of the material, you see basically the vapor pressure increases with the temperature. So increase the temperature, the vapor pressure will actually increase. And so this vapor pressure is very important because it is going to be finally determine the deposition rate, like how fast you can deposit the material. So so you see here basically that most of the material is actually evaporation is from melt only. So it means like here the temperature we are talking about for the most of the material, we will start basically the vapor pressure, which is having some meaningful number, is basically when their temperature reaches to their melting temperature only. So now we can think about some kind of model here. So you see, just for idea like how much deposition is there, one can actually even calculate like what will be the evaporation rate by having some kind of a simple models. So one of the model is like this is the mass evaporation rate, which actually this equation, this relation relates the mass evaporation rate with the molecular weight and as well as basically the vapor pressure of basically the melt liquid with the vapor pressure, partial PH is the partial vapor pressure of the partial pressure of the vapor in the gas. So means this is the so you can see here, if I this is the just the model only, so we can actually by putting some number here, we can calculate like how much will be the evaporation rate. Like for example, if I want to know for the aluminum, I know it's like the molecular weight, it is about like 27. Then I can use this equation, I can go back from the table. So you can see I can just I can from here I can obtain the like the 10 to power minus like around like this aluminum, though it is here. So this point is here, so I can have that the number here. So I can get the idea of the how much is the vapor pressure is there at a given temperature. So so means I can plug these numbers back to there, and then we can get the evaporation rate. So like how much will be the evaporation, how much material will get evaporated per second. So that can be calculated from the theoretically also. So now you see another point which is very important in this case is that basically the deposition rate which we are going to talk about. So if I want to calculate the deposition rate, how much deposition is there. So if means like first of all, how much total mass get lost from the source. So see, first thing is I can assume my source like a point source. Like my source is, if it is the point source, then what I need to do, this is my evaporation rate. So it means if this is my source, so I want to calculate basically how much total mass is lost, and this is my substrate which is making some angle here with respect to, this is my source, if I make a sphere here, so if my substrate is like making some angle which is actually theta with respect to the surface, this imaginary surface normal here. So what happens actually if I just so I have to basically integrate, this mass evaporation rate, how much total mass if I want to calculate over the time and over the total area. Over the total area I have to integrate over the time. This will give me the total mass which is lost, that is basically the ME now. Now if I'm using basically the point source, so per unit area how much mass it got is like deposited, that actually I can figure it out from that integral. You have to do the integral, it is not very difficult from the geometry. Then it shows you the cos theta dependence only. So if I say if my surface is actually a line, just like it's like a some kind of a surface is just, if my target is substrate is actually having some spherical geometry, and then in that case basically your theta angle will be 0, because if my substrate is having the spherical geometry, then basically theta will be 0, then cos theta will be 1, so you will get a simple number from the point source. But if I'm using a extended source, or sometimes we call it surface source, then you see we have to incorporate basically the azimuth angle also, because you see then the deposition, you can think of this surface source as the integration of multiple point source here. So means each time you have many point source. If I am thinking about the material which is getting deposited here, so there are another point from here the material will get, and it will be having some angle with respect to the surface normal. So there is another azimuth plane azimuth basically angle, which is also will also come into the picture, and that we are saying it is cos phi dependence. So for extended source, which is basically practically all the sources are extended sources, so we have a cos phi dependence here. So means depending on the point source and the extended source, your deposition rate can also differ. Now if I talk about the film, so you see in this case I am just taking a source here. You see this is my source and this is my substrate. So you see the material, this distance which is taken by the vapor atom is suppose h, and if the vapor atom which is going in this direction, this angle is phi actually. So so that's why this place, this center of the substrate will get actually will get more material in time compared to the corners actually. So it means if I keep on depositing this geometry, which is like the vapor flux direction, like this is the substrate is perpendicular to that, so you'll get more material. So you'll get basically some type of like you get more thickness at the center of the material. So this is the point here. And so if I have a point source, then this theta and phi will be same here. But if you have extended source, then your theta and phi will be different because there will be many sources. So you will get a different kind of like the equation for that. Now the film thickness uniformity, if I talk about, so you see here, so the maximum thickness will be at the center. We call it like d naught. If I just say this is d naught, then I can actually calculate basically how much will be the thickness. If I know from this equation, if I know how much mass was left from the source, then I can simply calculate, because I know this distance. I can calculate that. It is not very difficult. Simple mathematics, you can do that, and then you get basically the ratio of this the thickness, which is final thickness, at the thickness of the material which is getting at the center. So these two ratios by point source and from the extended source. So if you just plot that, actually these two, the ratio of the thickness versus the maximum thickness versus basically this height, the ratio of this height and distance from the center. So you see the material which is deposited by point source is like, you see, is like pretty uniform, comparatively uniform than basically using the extended source. So you see, still when this L by H is 0, L by H is 0 means the maximum thickness will be in the center, and the thickness will get varied as you move away from the center. That will always be the case. Either you use the point source or the extended source. But in this case, the extended source, that variation is pretty sharp compared to the point source. Now giving you the basically idea like how they look like, the source material, how the source material looks like. So see, we use material for thin film deposition, for thermal deposition, which is resistive heating. We use normally the materials which have vapor pressure, which can have the vapor pressure, reasonable vapor pressure at 1600 degree or C or below. Because you see, we cannot go for very high temperature here, because the reason is, if you use a very high temperature there, you just keep in mind inside the vacuum chamber, there is another like we don't have the convection loss, heat loss, because there is not much gas there. So and if you limit your, so it can be either conduction or through the radiation. So and the surfaces are very shiny also. So mostly basically this is radiation heat is very important there when we need to bring that down. That's why you see in the chambers normally we use some kind of a cold jacket to cool down the chamber, so that the material should not, the chamber wall should not get dissolving. If they start dissolving, then basically your the film will get contaminated also. So that is one of the drawbacks of thermal evaporation, because so we cannot go very high temperature. And the common material we use is gold, silver. Mostly these materials are used for the metallization part of the making some contacts, OMI contacts or Schottky contacts on basically the devices. So this is basically the different types of source here, and normally we use either the tantalum or the tungsten material. There are different shapes of the material. This like we call it like sometimes board. You fit your material here, and these two sides we just attach with some kind of electrodes to pass the high current. And these materials are highly, we call it like they are non-reactive material. So these materials, that's why we use for tungsten, because the melting temperature is very high, or so that actually you can use that. Tantalum is also very high. So these materials should not actually start like interacting with basically the material which you want to deposit. That's why we don't have much choice here. So there are only few materials we can use for the boat material. Otherwise, the source material can get contaminated here. Now, if we go inside the thermal evaporator, you see, I'm just showing you. So these 2 points are basically the electrodes. The electrodes, you see, the electrodes are tightened here, and these are the copper kind of the copper electrodes. So you pass the current, like we pass very high current here. So the current can be of the order of few hundreds to 400 nanometer, 400 amperes. It depends on like how much, what is the material you are depositing. And then we also use some kind, this is my substrate here, substrate holder here. So substrate holder is cooled by water, or it can be cooled by, in some other chamber it can be cooled by liquid nitrogen also. Then we have a quartz crystal monitor here, just to monitor the thickness of the film also. So you can have the idea, we can stop the deposition. Then there is some shutter, you can see this is some kind of shutter. So everything is sometime they are manual, sometime like they are automatic also. So when you get basically, when you get a signal from the quartz crystal that you get basically a particular thickness, this shutter will come in between the path of this substrate and the source. So you stop basically the deposition. So like I'm just showing you that part of the deposition which I discussed is like this is our deposition thermal evaporated inside the clean room. So this is like the water, this, so here we use in our, this is special geometry, we have 2 chambers, because, and we have we have designed this geometry so that, and locally made, so that we can get the vacuum in these 2 chambers by one single vacuum unit only. So when you want to use either of the chamber, or you can use both together also. So 2 separate chambers are there, but they are pumped by one vacuum system only. So in normal evaporator, you will find basically looks like same things will be there, similar things will be there. There will be a pumping station, there will be some gauges, some thickness monitor, and sample holder geometries will be there. So these are some of the things you can see inside basically the evaporator. Now, so this is just like we designed this system and gave to one company. So they have actually local company Indian company who just made the chamber for us. And so there are some automations also. So we have like 2 rotary, but one single turbomolecular pump, which actually can pump both the chambers in the same time. So so that's it maybe, and thank you for your attention, and I'm just will be happy to like answer your query if you have.
Thank you so much, sir, for your session. I would request the participants to either write in the chat box, or you may raise your hands. We will unmute your mic one by one. So Bhavanri has raised the hand. You can please ask your query.
Good evening, and thank you very much for the informative presentation, sir. Clear and explanation. Sir, I would like to know regarding the evaporation. You showed one picture which is in your lab. Another before that slide is like there is a boat which is having a wire where current is being passed.
This one?
Yes, sir. This one and before one.
This one?
Yes, sir.
Yeah. So what is your question, query?
The left one, crucible. You have the current which is passing through the crucible, and you have a source material, right?
Yes.
Could you please explain regarding that?
Oh yeah, so this is like, so this like there can be different type of geometry only. So here actually you see these are the current is passing through this, and we are actually heating this like, because sometime actually we just directly want, maybe sometime we use crucible, sometime we use like the wire also, like my material can be in the form of wire. So like sometimes, so those wires can directly go through here, or I can use some crucible, which is some kind of, you can think of some kind of a basket which can be heated to very high temperature. But the material of the crucible in such a way that it is like thermally conducting, but electrically it's not conducting. So it can go, once it can be heated, it can go to very high temperature also. So we heat this material and we just wind this wires over this crucible, because sometimes the material where you have is like you want the basically uniform heating throughout. Actually, you want to touch that, fill everything, you want basically the uniform heating. So that's why we prefer in this way actually. So it just, there are different types of sources that is actually based on the type of source you have. Sometimes we have source, my source is rod actually, then in that case you cannot maybe make the powder of it, then it is very difficult to fill in the boat like in this kind of geometry. Then you use this kind of spiral heated maybe spiral wires, and then you put your rod, whole rod like a wire inside this uh, spirals only, and you pass the current. So the geometry of the boat depends on the type of the source, like what in source is actually in which form, if it is a powder form, pellet form, or it can be your like the rod form. So that's, so that actually makes the difference here. Yeah.
Thank you very much, sir. Sir, I have one more thing, like you have showed the difference between sputtering and the evaporation. So
Yes.
which one is usually preferred, often preferred for fabrication?
So you see, if you just talk about basically the sputtering, the advantage of sputtering is that you can get you can very uniform film. First of all, the film is uniform because in the sputtering you can rotate the substrate. That is one thing. Another thing is basically the deposition rate is very high. I told you like the deposition rate in sputtering can go up to something like 1 micron also per minute. Whereas actually in the normal evaporation, either you use the thermal evaporation or the E-beam evaporation, it can be few angstrom per minute only, per second only. So that can few angstrom per second. So you can like few tens of angstrom maybe, or hundreds of angstrom per minute only. So that number can be maybe so your deposition rate is very high. That is one advantage. Another thing is basically in case of thermal evaporation or the electron beam evaporation, we normally they are done for the materials which has not very high melting temperature. The reason is because suppose if you use a board, because you need some kind of support, you want to put your material inside the board to evaporate it. So what happens, you are actually heating the board and that heat is getting transferred to the material. So there is a chance that the material, the source material can interact with the board material. So that is one of the another disadvantage of this kind of heat like thermal evaporation method. So the sputtering is preferred in that sense, like sputtering you get a uniform film, also you use the whole target. Now basically the material is coming out because of the high energetic ions only. So the surface is not actually, you are not heating the surface, so there is no heating there. So means like your chamber walls are also not getting heated, so there is not much desorption from there. So in those sense basically this sputtering systems are better in that case. So sputtering is normally used a lot, but for some materials, like if you want, if you really have the metals or something and you really want to deposit very thin film, because in this case when you want to use the sputtering you have to generate a plasma. So that plasma generation you have to introduce some external gas inside the material. So means you have to introduce, either make the argon plasma or some other plasma. So those gases has to be highly pure, otherwise you will get contamination from there. So because the actual deposition is not actually in the ultra high vacuum, you first do the ultra high vacuum, like remove the background residual gases, but then you introduce some gases there. So in that introduction the contamination can be there. So this is one of the drawback of the sputtering system, but normally in the industry we use if it is like for like context formation only, normally evaporation, thermal evaporation is used. But for the film deposition, if you want uniform film or something very high sputtering rate, then normally sputtering is used.
Thank you very much, sir.
Next we have Rama Shankarji. for the query. You can please unmute yourself.
Hello.
Good evening.
Good evening, sir. From this side, Ramashankar Gupta, sir.
Yeah. Am I audible to all?
Yeah, you are
Yes,
audible.
sir. Yes, sir. You are
Yeah,
audible.
madam, you can start sharing the PPT. I have sent it to you. I will explain.
My question is, sir, how the thickness of deposited film is monitored during vacuum deposition method?
Oh, okay. So,
My question is answered, sir.
I got your question. So let me just answer that. Actually, like it's like a very standard way. Like I can explain you. So the idea is I can show you basically. First of all, can you see the image picture here?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
We see a small, basically a kind of a small this unit where the laser pointer is there. So this is known as basically quad crystal monitor. So the idea is in the quad crystal monitor, this is based on the simple piezoelectric effect. So we have a quartz crystal. Quartz material is piezoelectric material. So what happens actually? So the piezoelectric material, if you basically put some kind of a electrical signal there, means you apply the maybe apply the potential difference along their optics axis, then you will get basically there will be strain generation inside the material because they show the piezoelectric effect. So what is done actually? So that actually means if I use some kind of external source and I have the which is having the resonance frequency of this piezoelectric crystals, each piezoelectric crystal is having its own resonance frequency, which is decided by the material property only. So means the piezoelectric crystal is actually resonating, mechanically resonating at particular electrical signal. Okay. Then what happens actually when this material get deposited on these crystals, their mass is getting changed. When the mass gets changed, their resonance frequency shift actually. So what is actually done in the instrument there in that controller? So they actually calibrate that, like how much, because the each change in the mass will give you the change in the frequency, and then from there the calibration curve they could able to figure out basically how much is your material is there. So the idea is quad crystal monitor, they use that. Yes.
Thank you.
The next is Surendra Kumar. You can unmute yourself.
Good evening, sir.
Yeah, good evening.
Sir, what is the minimum thickness, uniform thickness, which we can achieve through thermal evaporation and sputtering?
Minimum thickness.
Yes,
So
sir. Uniform.
So see, that depends on the type of the material also. See, one of the lot of people are having misconception also about the minimum thickness. It's a very good question. So let me just tell you, like even see, suppose if I am depositing gold, which is normally done for the contact formation, then what happens? You deposit the gold on, suppose I want to deposit gold on silicon itself. Okay, then
Yes.
how much thickness will get deposited? So you see, we are having two different types of material. So the gold thermal expansion coefficient which we are depositing and basically the silicon doesn't match. So what happens? Basically, so when you deposit the material, then still that equilibrium will never achieve, because they see the temperature, there will be always some thermal stress there at the interface. Because of that, if the more and more material you keep on depositing, so what happens, that thermal stress actually will be such that the material will start actually coming out, peeling off from the material.
Yes,
So
sir.
so that is the point. So normally we always use some kind of adhesive layer. You always use some kind of adhesive layer, like adhesive layer, which adhesive means that particular material likes both. It likes silicon and it also likes gold. So it likes some kind of bonding material. So first you deposit that, and then you deposit basically your contact material. This is one thing which I'm just telling you. This is another thing. So that's why the minimum thickness when we talk about is sometime limited by this fact only. Another thing is like the minimum thickness when we talk about. So see, Some materials, it depends on basically the material, because some materials the surface diffusion is very high actually. Like if you talk about the material like gold, which is having very high diffusion rate, so it actually goes inside the material also. Like their diffusion surface as well as the bulk diffusion is very high. So they actually, because you see the molecules are landing on the surface. In the thermal evaporation, what happens? The molecules lands on the surface, but they get a momentum also, means they get a particular direction, or they get some energy also. So they have to thermalize, means their energy has to be, their kinetic energy has to go down to zero only. Then only they will stop. Okay. And there is some energy which they are always getting because of the thermal energy, which is the room temperature energy, which or the temperature of the substrate. So because of that, actually molecules wander over the surface, and wherever actually it finally lodged, that will be some defect position where maybe there is some steps or some point defects are there, molecule will get lost there actually. And then, so actually overall your thickness depends on many parameters. It depends, minimum thickness depends on basically the substrate. It depends on basically the material which you want to deposit. So or basically the deposition rate also, like what is that, if you are depositing very slowly, then you can deposit, like in case of molecular beam epitaxy, the molecules are deposited very slowly, very slow. So they get actually there, and that they don't actually, you don't allow the surface diffusion, they get actually stick there. So in that case, see in thermal deposition, I think in general, like anything like getting less than basically 5 nanometer or something is not possible. It's like not reasonable. You cannot say it's a continuous layer. It's like just typical number I give. But if you go for atomic layer deposition, those things are meant for one molar layer, means one atom, 1 angstrom thick, I can make a continuous layer. So suppose if you really want a kind of a continuous continuous film over the large scale, or then people go for the atomic layer deposition. Like for the current technology, device technology, if you want a gate, like you want to basically gate oxide, you want to coat, or you want to, like I want to have aluminum oxide, titanium oxide, some gate material, then they use ALD, because if you want a very thin layer, you go for that. It will be continuous. So it's like I say it's like but the methods are different. Here you cannot go very small small scale. The reason is I just already told you, the material itself. Yes.
Yes, sir. Thank you. Thank you so much, sir.
Ishika, I think there is 1 or 2 questions in the chat. You can please take it.
Sure, ma'am. So the first question is from Dr. Satnam Singh. What is the film thickness deposition accuracy via evaporation process?
So the film thickness deposition accuracy actually depends on basically, see, the method itself by which you are you are actually like measuring it, like the QCM. I'm just suppose I'm using the quad crystal monitor. So they are highly accurate. Normally angstrom, up to angstrom level thickness you can get, few angstrom only. So they themselves are very accurate, but you have to calibrate it every time. Like you, when the material in the controller, you have to calibrate it, and calibration has to be there, but they are very good. You can get few angstroms only. So that thickness is very accurately you can tell. Yes, there is because they are based on the resonance phenomena. A small shift can be detected actually.
So there's one more question. If metal has to be deposited, then please tell the weight ratio to thickness of thin film which has to be deposited.
Let me try to understand the question itself. If metal has to be deposited, then what you are saying?
Please tell the weight ratio to thickness of thin film which has to be deposited.
Yeah, so normally I think how the deposition is done. So normally because there is a QCM, quad crystal monitor, which will tell you like how much material is getting deposited. So normally we fill the this kind of like our boat with some material, and then so there are some standards boards only. Like there are like in the market, you don't have the arbitrary kind of thing. So there is like you get 7cc boards, or you get like 15cc, depending on that. Like, or you are using electron beam, you get the crucible of 7cc, 15cc. Those are the very common one. So there is like nothing which is having the relation of the material which you are using or the weight with the thickness. Actually, the thickness depends on the deposition rate, like how fast you are depositing. Thickness depends on basically the temperature. What is the temperature? Like if I'm using the resistive heating, like how much current we are passing. So you have to, there will be some critical current over which basically after which the material will start melting. Only after that you will get some kind of a measurable kind of evaporation. Evaporation is always there at all the temperature, but the measurable I am saying. So basically the actual amount which you are using, it doesn't matter actually. It matters only how much amount get evaporated, and that evaporated material amount you have seen, like we have already discussed, it depends on temperature, it depends on the type of material, it depends on basically, suppose if you are using the thermal deposition, it depends on basically what kind, how much current you are passing. So those are the experimental parameters, but the weight of the material has no role in general in the final deposited film. Yes.
So we have another question. So please tell, if 50 nanometer thin film has to be deposited, then how much weight of metal wire to be taken?
So, see, you see, this mass is conserved. So you can, I'll just give this task to that person. He can do the back calculation. So you see, if you want to deposit 50 nanometer film, and if I assume it is a 1 centimeter square, so I can calculate how much volume will be there. So 50 nanometer into 1 centimeter square. Okay, you will get the volume. You know the density of the material. I know the density of the material. So you can quickly you can get back actually how much material is there. You see, if you, that will be negligible actually, because 50 nanometer thickness, then you get basically the 1 by 1 centimeter square. If I want to deposit, then you can calculate, you can figure out how much volume will be there. If I know the density, I can determine the mass. If I know the mass, I can use you can get the weight of the, then you know how much material you want to know, you want to get. That's not very difficult because density depends on the type of the material. But you see, basically there is a lot of loss actually. So there is a lot of loss, like means loss means like you material will get lost. It will not get deposited on the substrate, but it is actually, because I told you it is like a cos phi angle, so it is deposited because a line of sight. So atom will go and then deposit on the all the sides of the chamber. It is only small, substrate is only small. So if I go there, if I show you the image here, you see the substrate is here only, but there is another chambers are there, whole chamber is there. So your basically your material, most of the material is getting deposited on the chamber itself. So we get a lot of material get lost actually inside deposition over the chamber rather than actually on the substrate. So but you can calculate, you can calculate. It's a few, normally you fill the you keep on filling that boat, and you can have hundreds of deposition for small nanometer size. Yes.
We extend our sincere gratitude to Professor JP Singh for sharing his vast industry experience and technical expertise. Your insights have not only deepened our knowledge but also inspired us to explore new possibilities in this domain. Thank you, sir, for being a part of this program.
Thank you so much, sir. It was pleasure listening you, and I hope with myself we have learned many new things. Very informative session, I would say. The participants would have surely got much of the information from these sessions. So we will invite our next speaker, mm,
Okay,
Dr.
so
C. Ramachandra.
maybe I may leave now. Okay.
Yeah, sir, you can. Thank you so much, sir. Thank you.
Thank you for giving me
Thank,
opportunity.
yeah,
Thank you very
thank
much.
you, sir. Uh, Dr. C. Ramachandra, good evening, sir.
Good
Welcome
evening.
to our 6-day ATAL online FDP program.
Good evening.
After an insightful discussion on thermal evaporation in clean room, we now move to another crucial topic in semiconductor manufacturing: thin film deposition techniques under vacuum conditions. We are honored to have Dr. C. Ramachandra, Director Technical at 4C Tron, Bangalore, with us today. With 40 plus years of experience in wafer manufacturing, chip fabrication, packaging, and failure analysis. He has worked with ISRO, Silictronics India Limited, Micron Wafer Fab Singapore, and Tesla Semiconductor Limited. He pioneered VLSI circuit edit technologies in India and has trained professionals in clean room practices and semiconductor fabrication. Without further ado, I invite Dr. C. Ramachandra to share his expertise with us.
Good evening to all.
Good evening, sir. Welcome
Okay.
to the session. The stage is yours. The participants are eager to listen from you, sir.
Thank you. Thank you. The topic given in the brochure is vacuum deposition. I slightly modified. It is really thin film deposition techniques under vacuum conditions, because we are not depositing the vacuum. We are depositing thin film in the vacuum condition. So I slightly modified to make it more meaningful. Okay. Now, when we say thin film deposition, the first question comes, can we deposit in an ambience like atmosphere, or is it must that we have to use vacuum? The answer is, we can deposit the thin film in atmosphere. That means our real, this one. But unfortunately, scope is very, very limited. There are very, very few materials. So we are not going to touch upon that one. Rather than we are discussing thin film deposition vacuum, which is widely used in semiconductor industry. Now, when we say thin films, we would like to see what are the types of thin films, why thin film, what are the unique property it is going to exhibit, and some of the key requirements of thin film deposition that we must meet it, and various thin film deposition techniques. There are arrays of techniques. It is not one arrays. So I'm just trying to cover these things and various challenges and opportunities I would like to highlight. So in fact, we can classify the material based on thickness. In fact, we have divided the material on various reasons. Based on electrical conductivity, we say it is a conductor, semiconductor, insulator. Based on magnetic property, we say it is magnetic, paramagnetic, diamagnetic. Like that, each property we are going to divide the material. Then why not based on thickness? So when we want to divide the material on thickness, we can group it as a monolayer. That means only one atomic layer. Ultra thin film, which is typically about 0.1 micron. Then thin film, which is up to 5 or 10 micron. Then thick film, which is about 10 to 50 micron or 100 micron. Then bulk material. And one of the important characteristics of thin film is that they exhibit very large area to volume ratio. Very large, I highlight. And this is one of the fundamental reasons for thin film to exhibit certain unique properties. This is the key reasons which you will be seeing later. So they exhibit very, very unique properties, whether it is a mechanical or electrical, optical, thermal, magnetic, chemical, etc. So we are showing same thing actually, this one. These are all the important property we look from any material. Some materials we use it for electrical conduction purpose. Some material we use for thermal conduction. Some material we use for optical properties. So some of the material exhibits unique property in one or two domains. That is why we are more interested in studying thin film and fabricating the thin film. And most important thing is these property, these unique properties, they are not fixed actually. They are tunable based on the growth condition. That means we can engineering these properties to our requirement. So based on the growth condition. Therefore, optimization of the growth parameter, process parameter, they becomes very important because we are trying to optimize certain unique properties of the thin film. When we say mechanical property, we are interested in adhesion, yield strength, hardness, and many others. Similarly, when we say thermal property, we look for thermal conductivity, specific heat, thermal coefficient of expansion. When we say optical properties, we look for refractive index, polarization, transmission coefficient, reflection coefficient, absorption coefficient. When we say chemical, we look how good it is for corrosion resistance, how good it is for catalytic activities, etching, all these things we look forward. Magnetic means we look forward hysteresis, saturation, anisotropy, domain structures, etc. Electrical, we see how good it is in conducting the electricity, dielectric constant. So if you look into various material, when it is in the bulk state, they exhibit some property. Same material, if I have thin film, they exhibit entirely different properties. This may be due to the surface, large surface to this one, the area to the volume ratio. It may be due to the quantum effect, or it may be boundary, grain boundaries. There are various reasons behind this one, but basically the material properties of the material in the bulk state is quite different compared to the properties in the thin film, and some of these properties are quite useful to our application. That is why we are focusing on thin film. Now, if you look into the thin film as a system, sometimes we get very interesting, very useful property, very interesting. We classify them as we say it is a smart material. Sometimes the property is so good, we call it as a super material. But if you look from physics point of view or science point of view, it is basically abnormal material. We can call it any names, hot material, super material. Basically, these properties are not at all quite, it is quite different from the bulk. That is why calling abnormal becomes more logical. I will give the justification in the coming slides. If you look into the bulk system, any material you take, typically the number of particles in a system is much more than 10 to the power of 19. If it is a gaseous phase, if it is a solid, it could be 10 to the power of 22 or so. If it is a liquid, it is in between. There are very small intermolecular distance, the distance between one particle to another, and significant intermolecular collisions and interactions is continuously taking place. Therefore, basically it is a coupled and connected system, the bulk system. That means anything happens anywhere to one particle, it influences the adjacent one. The effect will be propagated. It is a coupled and connected system. And again, bulk system, if you look into the type of particle, it can have classical particle, it can have fermions, it can have bosons. If it is made up of classical particle, they follow Maxwell-Boltzmann distribution. If it is having fermion, they follow Fermi direct distribution. If it is a boson, they follow Bose-Einstein distribution. You may wonder why they are worried about distribution. That you will see the reason next. Most of the physical property, why most? In fact, all the physical properties, we can calculate, we can predict, we can compute precisely by knowing only two parameters. One is N, one is E. What is N? It is total number of the particle in a system. And E, it is a total energy of the system. If you know these two parameters, that means total number of the particle in a system, total energy of the system, then most of the physical property we can calculate, we can compute, we can predict. These properties, many of them, they include electrical conductivity, thermal conductivity, viscosity, magnetic susceptibility, heat capacity, modulus of velocity, so many things actually we can exactly predict. That means behavior of the bulk system is quite predictable, quite computable. There is no surprise, there is no shock. That is what I want to convey. That is why it is a normal material. When we say normal material, I knew it. It is going to behave like this. I know its specific heat. I know its magnetic susceptibility. All the parameters I can predict well in advance. That is why it is a normal material. Now, when we go to the quantum system, typically quantum system, the number of particles is very less, 5, 6, 10, or at most 10. There is a infrequent collisions or interaction between particles. It is a loosely connected system. Almost every particle is independent. And we apply principle of quantum mechanics to understand the behavior of this system. Principle of quantum mechanics, very, very accurate, though it is difficult to solve this Schrödinger equation for a number of 20, but the predictions are quite accurate. Again, physical properties can be computed. That means in the case of bulk system, physical properties are quite predictable, calculatable. It is a normal system. When you come to the quantum system, again it is computable. It is a normal system. Now let us see what happens when you come to the thin film. When you come to the thin film, number of particles is 1,000, 1,000 to few thousands, or could be even 1 lakh. There is a medium intermolecular interaction. The number of particles is too large to apply principle of quantum mechanics. I cannot use it for such a big system. But at the same time, it is too small for applying the principle of statistical distribution. Because statistical distribution gives very accurate results when number of particles is very large. Therefore, I cannot predict the behavior of the system. I cannot calculate behavior of the system either by using principle of quantum mechanics or principle of statistical mechanics. Therefore, it is difficult to compute or predict physical properties of a thin film system. I cannot tell its behavior. I cannot predict its properties. And because I cannot predict, whenever we get some strange property, we name it, oh, it is a spot material, oh, it is a super material. We could not have predicted. Could we predict it before doing the thin film deposition? No, impossible. Only after doing the experimental results, we get some surprising results. But you ask anybody, did you know this extra property, superior property, whether it is electrical conductivity or thermal conductivity before doing the experiment? No, nobody could predict. That means it is the lack of the physics that is now big constraint in predicting properties of the thin film. Okay, let us accept that one. Our science has not grown, physics has not grown to handle the thin behavior of thin film system. Now, anyway, thin films are finding lot of application. It is a must, so there is no chance. So we must grow the thin film. We must use it for our applications. Now, when we say we want to grow the thin film or deposit the thin film, it must meet various criteria. One of the important thing is thickness non-uniformity. Suppose you want to deposit 1 micron, what is the variation that is acceptable in industry? What is the tolerance you can choose it? Similarly, step coverage is how good it is to cover the step. Stoichiometry. Stoichiometry means if you are depositing one element, it is okay. If you are depositing multiple elements, can we maintain the composition accurately as required? And crystalline structure. Many times we want thin film to be crystalline, not amorphous. Not only crystalline, sometimes we prefer in some particular orientation. So can we do these things? So these are all the major and important requirements. And we see various techniques and what are the plus and minus of each technique. As I said, step coverage means if my surface is very plain actually, then every molecule, every point on the surface has equal probability of receiving the atoms. But if there is a step actually, then the side walls are very low probability of getting the atom. So thin film deposition is very poor here. Therefore, if I deposit aluminum, it may get disconnected, it can connect. I lose the connectivity at this step. So this is a step coverage, and it is one of the common problem. And we see what are the various ways to minimize this problem. Stoichiometry means if I want to deposit more than one element, how best I can control the composition. Suppose I want to deposit aluminum, I want to deposit titanium, I want to deposit chromium, and I deposit in a required composition. That is a stoichiometry. To any thin film deposition, there are basically 3 elements. One is substrate. This is the place, this is the sample holder on which I need to deposit. It could be silicon wafer, it could be gallium nitride wafer, gallium arsenide wafer, whatever it may be, that is the substrate. And target, it is the material from which we need to deposit. I want to deposit aluminum means that is the aluminum separate target. I may have to deposit chromium, so there will be target. Then environment. Environment in this case is a vacuum. The whole process basically flow of molecules from target to substrate. That's all. What we are doing is we are making the molecules to flow from target to the substrate and get deposited. So this is the essence of any thin film deposition. Now, what is the role of vacuum? Why do we need vacuum? How it affects? If we look into the mean free path, it is some constant divided by the pressure. And at the same time, if we look into the density of the particle, it is some constant into pressure. Therefore, if you have higher vacuum, you have larger mean path. Therefore, the mean free path should be sufficiently large compared to the distance between target and the source, the target and the substrate. But if I reduce the pressure, the number of particles also will reduce. In the process of improving the mean free path, I am losing the particle density. That means less number of particles means deposition rate will be less and it will take much more time. Much more time, it is not compatible to the industry. We cannot wait 1 day for deposition. It is not at all acceptable. It should be in a few minutes or so. Therefore, there is a optimization or compromise between the deposition rate and by this one actually mean free path so that films will be deposited. This depends on the chamber design and we need to work out. And thickness non-uniformity. Just last lecture somebody questioned what is the non-uniformity acceptable? In an industry standard, typically if you use 8-inch or 12-inch wafer, 5% is acceptable. It is impossible to have 100% uniformity, 100% the same. That means if you deposit 1 micron thickness, it won't be 1 micron everywhere. So totally variation, it should be better than 95%. So there are so many factors which affects. One is deposition rate itself will be fluctuating. The temperature gradient will be there at the substrate. Though you put some temperature, there will be variation. Substrate misalignment is the material. Material flux also, it is not coming, there will be some distribution. That means the density of the particle coming is not same from the target. And there will be some masking and shadowing effect. So there are various factors which we need to optimize to have a thickness non-uniformity which is better than 5%. So non-uniformity we can optimize by distance between target and substrate. Temperature of the substrate also it will affect. And one generally followed is rotation of the substrate. Therefore, while deposition, substrate will be rotating. Therefore, it averages out the variation. So these are all some of the techniques which are generally used. Now, coming to the deposition techniques, how do we deposit? That means material from target to the substrate. All the methods can be broadly classified under only 2 categories. One is PVD, another is CVD. PVD stands for physical vapor deposition. CVD stands for chemical vapor deposition. In PVD, there is no chemical reaction. It is purely physical. Whereas in CVD, there is a chemical reaction between target atom and the substrate. And each one of them has got their own advantages and drawbacks. And we'll just review various methods available in PVD and various methods available CVD. As we have seen just in the last this one, evaporation is one of the simple. Basically, we need to provide energy to the target material. Generally, target is a solid material. The molecules will not move by itself to the substrate. We have to provide energy. That energy we can provide either by thermal means or by electron beam bombardment. If you want to provide by thermal means, then the temperature of the evaporating material, it should be sufficiently close to the melting point. Need not be completely, because it depends on vapor pressure. I need to generate enough vapor pressure. For example, if I am using aluminum to deposit, melting point of aluminum is around 660 degrees around. So for me, any temperature less than 300 or 250, vapor pressure will be very less. So I will not have enough deposition. So I need to look for a temperature around 300 degrees approximately. so that I will have enough vapor pressure. And for aluminum, it is okay. If you go for tungsten, the melting point is much more high. So when you have a material like tungsten, where the melting point is in the range of 2000 degree plus, then I need to heat the evaporation material to that high temperature. That is a big challenge and big problem. You must realize vacuum system, high temperature, they are not at all good friends. They never go together. In fact, vacuum and low temperature goes together. That is why we use a lot of cryo traps to generate high vacuum. You want to have high vacuum, but you want to heat means it is very, very difficult. Therefore, the evaporation method is limited to the material which has low melting point, relatively low melting point. High melting point, it is not at all desirable. On the other hand, you go for electron beam, you are not heating the target material to such a high temperature. You are providing energy by bombarding the electron beam and making it to vaporize. So this is the essence of evaporation. On the other hand, sputtering means it is basically bombarding the target material by energetic ions such as argon, and it is a momentum transfer. For momentum transfer, you are creating a vapor of the target material which starts flowing towards the substrate. So another method is ALD. It is by the name as it says atomic layer deposition. That means this is the finest technology available for thickness control. At a time, only one atomic layer is deposited, it stops automatically. So if I want another layer, I have to go for second cycle. Another layer means third cycle. Like that, one by one atomic layer I can control. Perfect control on the thin film deposition. We have pulsed laser deposition. Here laser is used for providing the energy. Then we have molecular beam epitaxy. It is the highest end technology in physical vapor deposition. Then we have chemical vapor deposition, where there is a chemical reaction that takes place between substrate and the chemicals that leads to the formation of the thin films. And metal organics chemical vapor deposition. So these are the few techniques which are generally used in industries, and we'll quickly go through their plus and minus things. So there are various parameters which affects the performance and quality of the film. That includes substrate temperature, what is the binding energy, and how good the molecules diffuse on the surface. These are the important parameters that affects the performance of the film. And nucleation site on the substrate. Larger the nucleation site, it is a good for uniform film. And adhesion, after depositing, how strongly it is adhered. We deposit the films. If adhesion is poor, it will come out in the next process. So it is of no use. Then some application, we need a crystalline structure. So how do we get the crystalline structure? So these are the challenges we need to address. When we say physical vapor deposition, as I said, there is no chemical reaction. It includes generation of a vapor or plasma near the target. I have a target material. I need to generate vapor of the target material. So that vapor I have to transport from target towards the substrate. This has to be absorbed and deposited on the target material. So these are the three important steps. So how do we generate the vapor at the target material? How it get transported towards the substrate, and how it get absorbed and deposited on the target material. So this is important steps in any of the physical vapor deposition. So you can see we can have a thermal evaporation. As I said, thermal evaporation is good for material which has a low melting point such as aluminum, etc. And materials having very high melting point like tungsten, it is not at all advisable because we have to heat the target material to 2000 degree, which is then very, very difficult to maintain the vacuum because vacuum and high temperature, they never go together. On the other hand, sputtering, we are bombarding the target material by energetic ion. It is a momentum transfer. It is like, you throw a stone to the mango tree. If hit properly, the mango fruit will fall down. Momentum transfer. Similarly, energetic ion bombards the target material. If momentum transfer is effective, successful, the target material will fall down, even at lower temperature. Then electron beam evaporation, it is better than thermal evaporation because you are using electron beam to bombard the material. You are not using thermal energy. So at lower temperature, you can get the vapor, enough vapor pressure. And pulsed laser deposition, here you are providing energy by a laser beam, not by heating. So, and closed loop sublimation, you can use some materials which has a sublimation nature, then you can use that one also. So evaporation is a very old and very simple techniques. In fact, most of the academic institute, most of the universities, they prefer to have this one because it is easy to conduct the experiment. And it is a low-cost solution. Any research you want to do, generally we recommend people to start with evaporation because your aim is not to make a production purpose process, but you want to understand the process. You want to play with the system and understand and characterize. For that, evaporation is good system. Then comes sputtering actually. It involves bombarding the target material by energetic ions such as argon. So this is the next slightly complicated compared to the evaporation. Evaporation is very sensitive to the temperature, whereas sputtering is very sensitive to the vacuum because you want molecules to go and hit and transfer the momentum. That means molecules should move without any collision. Among them, there should not be any collision. Therefore, higher vacuum is required. You want molecules to move and bombard. Momentum transfer will happen only when molecules bombard. For that, free transfer should be there. Therefore, mean free path should be sufficiently good. Therefore, it is very sensitive to the vacuum. Evaporation is very sensitive to the temperature. So temperature should be near to the melting point. As it goes very close to the melting point, vapor pressure will be higher. If it is very far away, then the number of molecules are available in the vapor state is very poor and our deposition rate will suffer and we cannot wait hours together or days together for film deposition. So these are all some of the picture you have already seen in the previous talk also. You have a target material which is having crucible on which target material is there. We supply energy either by direct heating, then molecules will travel and get deposited on the substrate. Because we are directly heating material, now whatever the crucible is there, whatever the supporting material is there, that contamination also comes when temperature is high. That is one of the limitation or drawback of the thermal evaporation. Because if you are heating very high temperature, some molecules from the crucible or your holder will also get penetrated, get entered into the target material and they escape and reach the substrate. So impurity concern is there. And this target material comes with different shapes actually. It can be boat shape actually. This one, each shape has got its own advantages and drawbacks. It affects the uniformity, it affects the deposition rate, etc. We need to play with for different application, which configuration is well suited. So thermal evaporation, as we said, it suffers from contamination from crucible or the boat or sample holder actually. To avoid that one, we prefer electron beam because now the electron beam is generated completely outside. It is magnetically energized and taken and it makes bombard with the evaporant. So the temperature now is very less. So therefore it works almost at a room temperature. Because of the high energetic bombardment of the electron beam, these materials get evaporated. It is highly localized evaporation. So it is relatively cool, temperature is very less and also there is no impurity concern from the sample holder. That is the advantage of electron beam evaporation. But system will be definitely costlier compared to the thermal evaporation. So there are various system comes with nowadays system comes with quartz holder where you can measure the thickness, film thickness, and you can stop it automatically. Suppose you want to deposit 1 micron or 2 micron, you can tune it. After it monitor the thickness in line along with this one, and once it reaches thickness, it stops automatically. We have this kind of facility. It is an option. You want to have a inline monitoring or not, it depends on the cost, but it is available. Sputtering is generally we bombard with argon ion. Why argon means it is a inert actually. It does not react with this one. That is what we don't want some material which reacts and causes modify the material. So it does not react with the target material. We accelerate the ions, bombard to the target, and because of the momentum transfer, the target atoms get released. It is just like, as I said, throwing stone to the mango tree. If it hits the mango fruit will fall down. Momentum transfer and transport of the target atoms. So in evaporation, your provided is thermal energy. It is a momentum transfer. Thermal energy, temperature is the main requirement. Here, energy, momentum. Therefore, here we can work with low temperature. And whenever we say we can work with low temperature, it is a very, very plus point in thin film. Any process in thin film, if it is possible to work with lower temperature, it is highly desirable from the industry point of view. It solves many other problems. So it is a low temperature operation, and different materials have different sputtering yield. It is not that every atoms have same sputtering yield. Sputtering yield basically, as I said, it has ion generation, then sputtering, then deposition. This ejected from this is the overall steps or mechanism involved. And sputtering yield is number of atoms which get sputtered to the number of incident particles. Suppose one argon ion bombards the target material, how much target atoms falls down? That is sputtering yield. It varies from typically from 0.1 to 10, typically, but it can be anything else also. That means that is the very important thing, sputtering yield. Larger the sputtering yield, it is good. Our film deposition will be faster. But if it is very low, then we need to put more and more number of argon ions. And again, sputtering, there are different types of system configuration. We can use DC sputtering. This is good when my sample is electrically conductive. I can apply DC field. I can have pulsed DC sputtering. But sometimes my sample is dielectric, then I cannot bias it actually, electric. So I have to go for RF sputtering. And sometimes I can use ion beam sputtering. Instead of argon, I can use some ion beam sputtering, different ions. And we can use magnetron sputtering. That means sputtering, I am applying magnetic field so that it is more confined. Density of my ions will be much larger compared without magnetic field compared to. So if I apply magnetic field confines the ions. Therefore, my density will increase. When density will increase, number of argon ions sputtering will increase. So deposition rate will increase. But system is more complicated, more expensive. Then reactive sputtering. Some system, argon is chemically inert. It is possible to use some chemical species which reacts and makes it to fall down. So it is possible to use. It depends on the what kind of target materials we are having. Accordingly, we have to use proper chemicals. It is a reactive sputtering. So it is a simple chamber, and most of the time you don't need very high vacuum actually. Rough vacuum is good enough actually, and you need a power supply. If it is a DC power supply, if you want to, if it is a conducting material, or you must have a RF power supply if it is a insulating material. But it is a simple system, and any R&D or academic institute can have it actually. So DC sputtering is very simple. You have a cathode and anode. You need a power supply actually. You can, and you don't need very high vacuum. Typically 1 to 100 millitorr. It depends on this gap. Based on this gap, you have to work out actually. And it is good. It works very well with metals such as iron, copper, nickel. It works very well actually. So on the other hand, if you want to use insulator, then you cannot use DC, you must use RF. And when we say RF, we are not allowed to use all the frequencies. You must know industry is allowed to use certain frequency, and one of the frequency allowed is 13.56 megahertz. So you must have a source only of this frequency. You cannot choose simply some 20 megahertz or something like that. It's not allowed. There are certain licensing system is there. You must work with certain frequency which is allowed to use for industry. So magnetic transporting, so we are using magnetic field, we are confining the ions so that density will increase and deposition rate will increase, but it comes with extra cost of having a magnetic head actually, because we need to use a magnetic head and we need to confine the ions. So density will increase, obviously deposition rate will increase. This is a advantage is there, but again cost will increase because you must have a big magnetic field. The most today latest technology, or you can what you can imagine, what is the best system for thin film deposition is MBE. It stands for molecular beam epitaxy. This is the highest end of the system, and it is just impossible. You cannot think any academic institute. The very big high scale industry can only invest in this kind of system. It has a multiple sources in a single chamber. It is a very big chamber, multiple sources. Each one we call as a fusion cell, and the atoms will come out like a beam from each cell actually. That means I can have multiple beams coming from different cells. I can have a controlled deposition of multi-layers. That is the biggest advantage. And it has many built-in in-house monitoring system. It can tell what is the composition, is it crystalline or not, is it thickness, what is the thickness, continuous display will be there. Therefore, you don't have to, you just program what is required, what is the structure we need it. So multi-layer structures you want to deposit, and this is the best solution, but very expensive. One cannot think of it is used mainly in very, very big industry, and it works in ultra high vacuum. So there are various effusion cells. It depends on the system. You can have 1, 2, 3, 10, many things. There is a substrate will be there actually. The molecules will be coming like a beam operated. It's focused everything on the target. You can address, you can activate molecule from one species, after that another species, after that another species, or you can have a simultaneous deposition from different effusion cells. It depends on what kind of structures you want to make. That is the biggest thing actually. And whole thing is now system, there are various in-house monitoring system, spectroscopic equipment. So you will be knowing thickness, you will be knowing layer composition, you will be knowing crystallinity. All important parameters are measured while the film is being deposited. Therefore, it is the best system one can imagine or one can think. But again, it is beyond the scope for any R&D or even academic institute. It is used only very, very high-end industry sector. There are a lot of research work is going on. As I said, critical requirement is ultra high vacuum actually. Then effusion cells, it handles typically 6 to 10 effusion cells actually. Substrate holder, which is made, temperature can be controlled, which is made to rotate during the growth to have uniform. So we can control the precise temperature, and there are many inbuilt spectroscopy such as reflection, high energy, electron diffraction. It monitors the surface structure and the growth through mode. Therefore, you don't have to correct. You can just monitor. So, molecule beam generation, there are various effusion cells and beam interaction with substrate, and layer by layer growth. We can have a hetero structures. We can have multi-layer structure in a single shot. So there are, it is used for depositing semiconductors, metals, various metal like aluminum, silver, iron, oxides like aluminum oxide, titanium oxide, magnetic materials like iron, cobalt, nickel, and various other compounds. We can even dope the metals which are in heterostructures. Atomic level impurity we can introduce. It has various applications. The HEMT transistor, high electron mobility transistors are requires heterostructure growth, and it has been realized. Quantum well lasers, it has been realized. Very precise LEDs and lasers are realized actually. And today people are working on optoelectronics, nanotechnology, spintronics, quantum computing devices. All this area, it cannot be done without the MBA technology. Advantage of MBE, as I said, it is an atomic layer, very precision, and multiple layer heterostructures can be done. Very high purity because we are using ultra high vacuum, so there is no chance of having any impurities. We can use versatile of materials. We can use semiconductor, we can use metals, we can use dielectric simultaneously in the same chamber, and we can create abrupt interfaces. So these are all the important advantages. There are various innumerable applications like this one, it is their quantum well heterostructures actually. And today people are working on various LEDs for commercial and industrial users, solar cells, photo detectors, all these things. It is an open area actually. One can think of fabricating any device and structures using MBE. So magnetic materials, superconductors, and various other quantum dots have been fabricated using MBE. It is just like a open research. The key advantage is atomic layer precision, very high purity, which we cannot think in other techniques because we are doing deposition in ultra high vacuum chamber. Very versatile, abrupt interfaces can be, and complex heterostructures can be realized. So people are working on qubits, quantum devices, high performance, low power transistor, LED laser devices, spintronic, and novel materials for solar cells. These are the lot of areas where active work is still going on. But as we said, it is limitation means it is very, very high cost. An academic institute or even R&D institute cannot think of. It's a very huge investment. Not only equipment cost, the maintenance, calibration, dedicated engineer, it requires separate team. So one cannot think easily. Low throughput, it is a very slow process. And poor scalability. That means today you have a system for handling 4-inch wafer. Tomorrow you want to do for 8-inch wafer. It requires a huge effort actually. You cannot simply scale it. You cannot simply increase the size of the chamber and do the same process. Lot of optimization has to be done. So scalability is very cool. And inadequate process control. Every time we need to optimize actually. So it is not fully automated. Okay, these are the references you may get it actually. Another technique which is very again popular is pulsed laser deposition. And its advantage is deposition of complex material, deposition of compound material, and excellent stoichiometry control. What do we mean by stoichiometry control? Suppose I want to deposit aluminum. No problem. I can deposit aluminum. If my target material is aluminum, what I'm going to get is only aluminum. Suppose I want to deposit aluminum, chromium, nickel, tungsten, some 3-4 elements with certain composition. Then it is important that that composition has to be maintained, and that is possible only in pulsed laser deposition. Here they are providing very, very, very high energy for short time. Therefore, the high power short pulse laser is used. The material, I believe I am audible to everybody. Am I right?
Yes, sir.
Okay. High power short pulse laser. So we are providing very high power short pulse lasers. It completes the whole material. It does not matter whether melting point of aluminum or tungsten, or it does not make a difference. Such a high energy we are providing, all the material get ablated and forms a plume. And once this plume get transported towards the substrate and get absorbed and deposited. That means whatever the material composition is available in the target material, same get transported to the substrate and get deposited. There is no change. If you use other method, for example, if you use sputtering method, what happens? Sputtering yield of aluminum is different, sputtering yield of chromium is different. Therefore, percentage of deposition of aluminum chromium will be different. Similarly, if you use evaporation, then vapor pressure of aluminum is different, vapor pressure of tungsten is different. You do not get same quantity. Here, these differences are wiped out actually. You are providing such a high power laser pulse, everything get ablated. Difference. It is like a earthquake. When earthquake happens, ant also will die, elephant also will die. It doesn't make a difference. So similar here, such a big shock comes, then everybody get ablated, everyone. So then everybody gets, that's the plasma roommate transports. Therefore, whatever the composition in the target, replica will be deposited. And this is the only way, only technique today proven if you want to have very good stoichiometry. So some of the development is in 1980, we could develop excimer laser, that is the beginning of, and 1987, we have done high temperature superconductor using this technique. And in 1990, systems have been developed with pulse widths of nanosecond, then picosecond, and femtosecond. Today, we have pulsed laser systems with femtosecond laser, such a short duration. So in femtosecond, one atom cannot make any difference with other. Such a high power energy comes in such a short time, then every atom gets ablated. There is no time to even transfer the energy to the neighboring atoms. So you can see a laser beam coming and bombarding the substrate actually. It's a pulse of very short duration. Materials get ablated and deposited on the other material. Again, it happens in the vacuum chamber. So basically involves absorption of the laser, formation of the plasma, and transport of that plasma, and getting deposited, getting nucleated on the substrate. All these things are important parameters. You can see nucleation and growth is very important. Your substrate should have enough condition to absorb and create a growth of these films. Many developments have taken place. We have done diamond-like coating, superconducting films, single-wall nanotubes. It is easy to have multi-wall nanotubes, but growing single-wall nanotube is always a challenge, and that has been successful using these techniques, and graded coatings for corrosion and thermal barriers. These are some of the recently done work on this field. Then, as I said, the ultimate in thin film deposition, as far as thickness control is there, it is atomic layer deposition. What is atomic layer deposition? Only one atom layer. So there is no question of thickness variation. It is 100% uniform because I am depositing only one atomic layer. If you say 1 micron thickness, it will have several thousands of layers. So here only one layer is deposited in one cycle. If I want second layer, I have to go for second cycle. If I want third layer, I have to go for third cycle. It is basically possible because of self-limiting surface chemical reaction. This is a chemical reaction which self-limits by itself. Then it has very low pinholes and particle contamination, excellent step coverage, even inside high aspect ratio structure. So it is very, very developed technology and utilized in many of the applications. So we could grow oxides, we could grow fluorides, we could grow nitrides, we could grow metals, we could grow sulfides. Various metals have been developed. What is the important factor or requirement is to having proper precursors, developing proper precursors. If we do not have precursors, then we cannot grow this one. For any material, I must have a proper precursor. So there are various precursors have been developed actually for different material. Today we have a libraries of thousands of precursors. For a given material, I can choose that precursor and develop. So it basically apply precursor to the surface, precursor get absorbed, then apply passivation layer, then again purge, that will go. Then one cycle is completed actually. One cycle is completed, chemical reaction stop. Because this is a surface limited chemical reaction. Precursor absorbed by the surface then reacts with the chemicals. Once the reaction is completed, No more further reaction. Already it is saturated until I apply another cycle actually. Therefore, in a given cycle, only one atomic layer is deposited. It is a self-limiting chemical reaction, surface reaction. This is very, very good, excellent in controlling the thickness of the thin film. So you can see precursor coming and moving toward the substrate. They get absorbed in the surface. Then we are applying purging chemicals to interact with surface. Then we purge out whatever is not required. So whatever is required, it gets absorbed. So conformality and uniformity. So it is very, very conformal. Many complex structures, 3D structures have been deposited using, it is a self-limiting reactions, so we don't have to worry about thickness control. Only one layer is deposited. And high aspect ratio structures, many structures having high aspect ratio, it has been deposited because it is a surface reaction. It gets absorbed by the surface and reaction happens only at the surface. Precise thickness control, because there is no variation, only one atomic layer, and it is linear growth. Some of the common precursors have been developed actually already. Precursor selection is very important, and precursor pairing, that means what precursor you are doing first observed on the surface, what precursor for chemical reaction. There are various precursors which have been identified, for example, TMA, trimethyl aluminum, and water for aluminum oxide. Then there are so many TDMAT or titanium oxide, hafnium tetrachloride. There are various library of precursors are available, and today it is still a open research. In fact, this is one area academic institute can focus, because doing research on chemical is not expensive. You can have a small laboratory, you can work out on different precursors and see how good it works with some materials, like maybe aluminum substrate, silicon, or copper. You can work out different precursor and identify how well it reacts and forms a film. It finds various application in high-K dielectrics, barrier layers, DRAM capacitors, etc. And today, without ALD, many of the work is not at all, many of the industry cannot run. It depends so much on the ALD applications. So even optical coating, energy storage devices, catalytics, MEMS device, everywhere ALD system is used actually. As I said, precise thickness control, excellent conformality, uniformity, because only one layer, there is no variation. And it is relatively low temperature process. And as I said, low temperature process is highly welcome in industry. Whenever you have a vacuum system, if some process can be done at lower temperature, it is highly valued in industry. Of course, it is a very slow deposition. As I said, in one cycle, only one atomic layer deposits. If I want second layer, I need to do again. And precursor availability and cost. Today, we have a library of precursors. Still, we need to develop various precursors for different types of substrates and material structures. And its cost and precursor complexity. And precursor, it should not create another chemical compatible with other materials. Reference, okay. So some of the example we are done in industry, I will show the image of the ALD. This you can see it is a DRAM. DRAM means dynamic RAM memory. Basically, it has a two conducting plates. Inside is filled with insulator. So this is the poly plate. This side is poly. Inside you can see aluminum dioxide, which is used for a dielectric. So it is a deposition done using ALD system. Actually, you can see how well it is conforming throughout the region. It is a used in DRAM. Similarly, gate oxide. If you consider any transistor, gate oxide will be there actually. This is a silicon lattice. You can see individual silicon atom. Somebody says, can we see individual silicon atom? Optical microscope, it is not possible. But using transmission electron microscope, you can see individual silicon atom, which is very well closely spaced. It is a crystalline structure. Then we have a gate oxide, which is silicon dioxide. Then we have a polysilicon of different varieties. It is very important to grow this oxide and control this thickness. This thickness variation causes lot of problem. If it is too thick, transistor becomes cold, difficult to fight. If it is too thin, transistor becomes hot and leaky. So maintaining this thickness is very, very important. So this is done using ALD system. This is a transistor structure. You take any transistor actually. When we say gate, actually, we have a polysilicon, this is layer, this is a tungsten, again we have nitride, we have again polyplug. There are so many layers. So you can see how precisely, how accurately it has been deposited. These are all in the nanometer scale. Then ALD today, it is coming with some attachments. PEALD means plasma enhanced ALD. So because now energy we are giving through the plasma, it is a low temperature and low surface damage. That is the advantage of the thing. And ALD used for quantum devices, gallium nitride power electronic devices, peroxide solar cells. So these are the important applications of ALD. So far whatever we have discussed, it is a physical vapor deposition. In physical vapor deposition, there is no chemical reaction between the target material and the substrate. So whatever the target material is there, same thing will get deposited. But when we come to the chemical vapor deposition, there is a reaction, chemical reaction. Now let us see what are the advantages and what are the limitations. It is useful for wide varieties of materials. It provides excellent stub coverage. Stub coverage is one of the major limitation or major challenges in physical vapor deposition. Here that problem is almost removed, mitigated, because there is a chemical reaction which takes place everywhere at the surface. Therefore, wherever chemical reaction takes place, materials get then deposited. Because chemical reaction is involved, stub coverage problem is not a problem in chemical vapor deposition. So it is widely used process in which films are deposited by a chemical reaction. We are using certain chemicals to deposit. For example, I want to deposit silicon nitride. What I use? I put silane, make the chemical reaction with ammonia, and silicon nitride is deposited, hydrogen is put. The important thing to observe is the incoming chemical that should be in the gaseous form. If it is in the solid form, it is of no use. Even liquid form, it is not a good choice. So preferably it should be a gas because it is easy to control the flow of the gas in a very precise manner. Another important thing is this product which we need, it should be a solid which should get deposited, and byproduct should be a gas. If byproduct is not a gas, suppose it is liquid or solid, then it becomes very difficult to remove from the vacuum chamber. Therefore, selection of the chemistry is very, very important. You may find different chemistry for depositing silicon nitride, but the question is whether inputs or the gases you have to verify. Byproduct is a gas. If it is not there, then even though that has other advantages, we reject it because if it is byproduct is not a gaseous form, if it is liquid or solid, it stays in the chamber and it becomes a big headache for the production purpose. Therefore, selection of the chemicals is very, very important. So within CVD, there are different sub branches. We can have atmospheric pressure CVD. That means chamber is kept at atmospheric pressure and chemical reaction take place. Or we can use low pressure, or we can use plasma enhanced CVD, photon, that is laser assisted CVD, or metal organic CVD. Each one of them has got their own advantages, merits, and limitations. So when we say atmospheric chemical vapor deposition, we do not generate any vacuum. So it works at atmospheric pressure or very close to that one. When we say low pressure chemical deposition, we don't use high vacuum, but not atmospheric pressure, very low, maybe 1 torr, 10 torr, something like that we use. When we say plasma enhanced chemical vapor deposition, we are using plasma to support the energy. Therefore, the reaction, chemical reaction take place at a much lower temperature. Suppose I don't use plasma, I want to deposit silicon or silicon dioxide. Suppose the process temperature is 700 degrees centigrade or 800 degrees centigrade. If I use plasma, then the process temperature will reduce to around 300 degrees. And I always told actually in vacuum, low temperature is highly welcome. We respect it, we welcome it from the production point of view. Any process, you say it works with low temperature, we don't mind spending more money, but we welcome it. That is the advantage of plasma enhanced chemical vapor deposition. So these are all some of the comparison. APCD means atmospheric speed, simple reactor, fast, then poor step coverage. Then LPCVD is excellent purity, uniformity, high temperature, low deposition rate. PECVD, the biggest advantage is low temperature. If the temperature in normal CVD is 700 degree, here it will be reduced to 300 degree also. And it is very big advantage from the production point of view. So you can see the simple configuration. There is a gas inlet, there is a gas stream, then after reaction that gas will be exhausted out. It's a very simple chamber relatively. Again, LPCVD is same, but only thing is you are generating certain vacuum because you need certain, it is not atmospheric, you need to create certain vacuum in this one. That is the low pressure. In plasma enhanced chemical vapor deposition, you are generating plasma and we generate plasma using RF power, which works typically 13.5 megahertz actually. So because we generate plasma, we are providing energy by ions. So chemical reactions will be much faster and much higher speed, and operating temperature will be much lower compared to the without plasma. That means ambient conditions. So it is a simple actually. You have RF chamber, wafer, so these are all the sources of energy. If you use CVD ordinary, main source is thermal. If you use MOCVD, again thermal, but specific this species are organometallic. PECVD, it is ion. We are providing plasma, therefore it is plasma plus thermal, works with very low temperature. And PCVD, photon, it works with low temperature. You are using laser beam and atomic layer deposition, you are using thermal and light monolayer. So these are the comparison of different CVD processes. Basically, whether you take any CVD, these are all the important steps that happens. Whether you take atmospheric pressure CVD, LPCVD, or PECVD, whatever the CVD you take, the first and important thing is controlled injection of precursor to the chamber. So the precursor should move into the chamber in a controlled manner. The rate at which it moves is very important. That is why we don't allow it in the gaseous form directly. We use mass flow controller. It should be precisely controlled. If you don't control it, you will not get the desired results. The transport of this precursor to the substrate, then these precursors should get absorbed by the substrate. If they flow, if they simply enter the chamber and exit out, it is not doing any job. It should get absorbed. Therefore, selection of precursors is very important. You need to make sure that it gets absorbed by the substrate. And once it absorbed, it must diffuse to the on the surface. And it should chemically react with the substrate. And whatever the byproduct is generated, that should be in the gas form, that should be driven out by the exhaust. So these are all the important requirement for any CVD. Therefore, selection of the precursor chemical is very important. If it does not satisfy any one of these conditions, then that chemical we cannot use it. So precursor should have good volatility, should flow easily, you should have good thermal stability. That means you should not decompose. If precursor should decompose, sometimes I may be working with 300 degree, 700 degree. If precursor decomposes, it no more remains as that chemical. And you should have clean and controllable decomposition of the substrate. And byproduct should be volatile, very important. Otherwise, byproduct falls on the sample, it creates like a contamination. And it should be preferably non-toxic and preferably non-pyrophoric. Non-toxic means it should not create any health hazards. Non-pyrophoric means it cannot catch fire, but unfortunately, it is difficult to meet all these requirements by any given precursor. Quite a number of precursors we are using in industry are quite toxic. It is again an open challenge to the academic and R&D institute. Can you find a substitute for the precursors which are not toxic? Okay, which does the same job. Similarly, some of them are pyrophoric. For example, silane is very dangerous. The moment it comes out, it catches fire. Therefore, can we, instead of silane, can we use some other equivalent which does the same job? These are all the R&D opportunities one has to think. It does not require much expensive. You have to think and come out with solutions. Typical applications CVD to use it for hot coating, special glasses, solar cells, artificial diamond, in semiconductor industry widely used, and carbon nanotube, it is being widely used. There are various pairs of precursors already established actually. So these are some of the examples. If I want to deposit gallium arsenide, then we use these two. If I want to deposit tungsten, we use these two. Or I can use even this one. If I want to deposit silicon dioxide, I use silane and oxygen. And as I said, silane is very, very dangerous gas. It is pyrophoric gas. It catches fire. Then titanium, can use it. Different silicon nitride. Different, there are libraries of precursors. And it is open. One can still, explore with different precursors. Precursors get sufficient energy in the plasma state. Chemical reaction takes place at reduced temperature and significant reduction of operating temperature. It is very, very highly recommended in any vacuum system. If I can reduce the operating temperature, it is a very plus point for industry. PCVD means I am using laser to provide additional energy, and chemical reaction here also take place at reduced temperature. And because it is a laser, I can focus it on certain specified region and make it to work in that region. So another important thing, latest development is MOCVD. What is MOCVD? It is metal organic chemical vapor deposition. See, most of the metals, they have very high melting points. As I said, aluminum is around 660, tungsten, there are more than 2000 degrees. So it is very difficult to deposit this material. I need to heat it very high. But it is possible to use this metal in organic molecules. I can impregnate these metals in organic, this one, and at low temperature, I can, almost at a room temperature, I can deposit. Then I can drive away organic polymers and make only metals to get deposited. It is very tricky job actually. So very, very low temperature. Even tungsten, I can deposit less than 100 degrees centigrade. So it is a low temperature deposition. I can deposit metals having high melting points. If it is tungsten, I don't need to heat to 2000 degrees. 100, 150 is good enough. Metals are imperative in organic radicals, and we deposit these organic radicals and we break this organic chain by some ion bombardment and vaporization transport of these precursors. So this is an indirect way of depositing metals or any materials having very high temperature of melting point. It is a low, easy or tricky solutions. So there are MOCVD, it is very high purity, it provides actually precise control in terms of thickness, composition and structure actually. And people have grown epitaxial. Epitaxial means same crystalline orientation, crystal alignment with respect to substrate. Now a lot of research has happened. Now today we can see libraries of precursors available for various precursors are already been identified, but it is an open area. Still you can try with different precursors which have some different advantages. For example, we use trimethyl gallium, we use arsine, we use trimethyl indium. You can try with different types of precursors and study this kind of advantages for depositing this material. It is an open research area. So it is basically, we are depositing the precursors actually to a gas inlet actually that get deposited. Then carrier gas is there actually, which is flown through a mass flow controller. Then we heat after chemical reaction, heat it to drive out the organic molecules. So substrate heating is required to drive out the organic molecules. Chemical reaction is very important between the precursor and the substrate actually. Film growth is very slow, but it takes place. And controlling the temperature, pressure, and gas flow rates are very, very important. It is possible to grow epitaxial layer also in MOCVD. What is epitaxial layer? Suppose you have a substrate with some orientation, then I want to have same orientation, it is possible to deposit. MOCVD reactor has precursor source, very important, which is bubbled through our vaporizer, it is injected. Mass flow controller, I can control the flow of the masses, reaction chamber, substrate holder, exhaust, and these are the important elements. So today we can deposit metal, semiconductors, oxides, nitrates, and many other. So number of materials we can deposit is increasing, and probably it keeps on updating every 3 months. You can see the research papers. Many materials have been deposited. So there is always an open source of research for developing new precursors for MOCVD. You can work with some different precursor which has an advantage in terms of cost, in terms of safety, in terms of handling. And one of the important thing is in situ monitoring. Can we monitor the performance of the chamber, film thickness, and other parameters in situ? Reactor design and how do we improve the uniformity? So there are various references. There are many challenges overall if you consider the thin film area. To determining composition and structure of the thin film in situ and offline. I deposited some thin film. While depositing, is it possible to confirm? Is it possible to measure its composition, structure, crystalline structure, orientation, etc. So that I don't need to waste. If it is, I want to deposit 100, if it is going on 110, some other direction, I need to stop and I don't want to waste the material. Is it possible to this one? Is it possible to measure thickness? As thickness, it is possible already. System is here. Another problem is computation of refract index of multi-layers and heterostructures. Today, you might be knowing actually one of the way of for measuring thickness is ellipsometer, standard equipment. But if you use ellipsometer, you have to feed the input. What is the refractive index of the film? For simple material, it is okay. Suppose glass, I know refractive index 1.5. But when you have a multiple layers, it is very difficult to tell what is the refractive index. When I have multiple layer, different materials. So if I don't feed the refractive index, it cannot tell. It can tell the refractive index if you provide the thickness. Now, it is something like solving two variable in one equation. I say xy is equal to constant. Now I must know x so that I can calculate y. I must know y, I can calculate x. So if I know refractive index, I can calculate thickness. If I know thickness, I can calculate refractive index. But multi-layers and heterostructures, how to compute refractive index and feed it. It is one of the challenge today. It is also there. Various models are coming. People who are developing refractive index, they are coming with various models. In fact, today cost of the refractive index is more than 20 to 30 lakh. But hardware part is less than 1 lakh. Most of the things are coming out with this kind of models. So can we develop a model so that it addresses refractive index of different layers? Then most of the thin film deposition is horizontal, planar. For some application, some part I want vertical structures. So is it possible to deposit vertical cavity structure? See, there are various challenges. I'm just highlighting. It doesn't mean it is only limited to this one. So subject is open. Academic institute, research institute, they can think in any dimension, but lot of opportunities there. Opportunities are unlimited. So that is what I wanted to drive in this lectures. Okay, this is my contact details. For any help or support, I am accessible. I am staying in Bangalore. Thank you all for listening patiently.
Thank you so much, sir.
Yeah.
I would request the participants to raise the hand or write their questions in the chat. It will be taken one by one.
Sure, sure.
Yeah. Any questions? Yeah, there are some. Okay, yeah. Bhavanari, you can please ask your question.
Please, please ask your question. I will try to answer.
Thank you, ma'am, and thank you, sir, for your clear presentation and also the opportunities in the upcoming semiconductor industry in India.
Yeah.
So, sir, I would like to know few things like if I want to grow a dielectric at
Yeah.
a lower temperature, what could be
Yeah.
the best process? Also, in the molecular beam epitaxy, you have
Yeah.
shown different sources, how the
Correct.
composition could be varied. Another one is like if you want to know regarding the vacuum systems, design of vacuum
Okay,
systems.
let us try to address one by one.
Yes,
You
sir.
said dielectric constant at this one. See, once you use a dielectric constant, so if you use evaporation, it is always a high temperature. Sputtering, relatively lower temperature. I told sputtering does not require temperature. So if you want to choose the lower temperature, sputtering is a better choice. And because it is dielectric, you have to go for R sputtering. You cannot use DC sputtering. And if you want to increase the deposition rate, you have to go for magnetron, so that it is sputtering plus you are applying magnetic field. So you have a higher deposition rate. Each thing comes with a cost. Am I made it clear for dielectric?
Yes, sir. Thank you, sir. Sir,
Okay, what is the next question?
Molecular beam epitaxy, you have
Yeah.
different sources, right? For depositing.
Diffusion cells. Yeah, you have to opt for while buying actually. So generally, system comes with 5 diffusion cells, 6 cells. You can even go for 10 cells, depending on the cost and budget you are going to have. How much cost you are having? It is very expensive.
Thank you, sir. Sir,
You can have
also,
more, but each thing comes with a cost. But very
sure.
precise, utmost precision control, multi-layer heterostructure is possible only in MBE.
Thank you, sir. Sir, also, if you want to learn these processes
Yeah.
on system design or vacuum
Yeah.
system design or
Yeah.
development, could you
Yeah.
suggest some books which we can refer, because there are a couple of references in your presentation. If you could suggest one or two books that could help us to
I
learn.
don't remember right now, but you share me your email, I will forward it. There are many
Definitely,
books.
sir.
There are many books available. Vacuum technology.
Sir, yes, sir.
Yeah. Right
I
now I
will email
don't
you.
remember, but I will try to send you by email.
Thank you, sir. I will email you, sir. Thank you very much.
Yeah, so the next one, Rama Shankar, you can please take forward your query.
Hello.
Rama Shankar, you
Yeah,
can
please.
Yes, ma'am. Good evening, sir.
Yeah, please tell me the question.
Sir, how we achieve ultra high vacuum, sir?
Okay, very good question. See, when the vacuum level is something like 10 to the power of minus 1 torr, that is the required vacuum, then rotary pump is good enough. When we want to achieve a vacuum of 10 to the power of minus 3, minus 4, minus 5, either we use diffusion pump or turbomolecular pump. Nowadays, diffusion pump nobody is using because it uses oil, it leads to a lot of contamination. Therefore, turbomolecular pump is a choice. So that generates vacuum in the range of 10 to the power of minus 4, 10 to the power of minus 5. Then, if you want 10 to the power of minus 6, minus 7 in this range, rotary pump is required, then turbomolecular pump, then support with cryo pump. That means cold traps. That generates vacuum up to the 10 to the power of minus 7. You want still higher vacuum, 10 to the power of minus 9, minus 10, then sublimation pumps are used. Very high, ultra high vacuum. So there are various, in fact, one of the topic is generation of the vacuum pumps you have actually. I believe they will cover starting from rotary pump, turbo pump, then cryo pumps and sublimation pumps. There we can generate vacuums of utmost preference, but everything comes with a cost. And it depends on the chamber size also. That is why we don't want to depend unnecessarily increase the chamber size. Then my cost of the vacuum will go up.
Thank you, sir. Sir, can you share your PPT, sir?
No, it is already sent to the your university. You can already download or take from them.
Yeah, it
I
will be
already sent it.
PPT and will be shared to all the participants.
Please help. See, I strongly believe knowledge sharing. Nothing to hide actually. I am
Sure,
happy
sir.
if somebody, if knowledge becomes useful, I am very happy.
Right, sir. Sure. We will be sharing the PPT to all the
If somebody does
participants.
not get it, you can mail to me. I will send it.
Yeah.
Thank you very much, sir.
Okay.
Any other questions from the participants? Ishika, you can check if there is any questions in the chat box.
There aren't any questions right now.
Yeah, okay. So I think, sir, we can wind up now if there are no further
Okay.
questions.
Thank you. Thank you
Right?
very much.
Yeah, Ishika, please take it forward.
On behalf of everyone attending, we would like to express our heartfelt gratitude to Dr. C. Ramachandra for delivering such an informative and engaging session. Your expertise, insights, and thought leadership have made this an incredibly valuable experience for all of us. Thank you once again for your time and dedication, sir.
Thank you. Thank you.
Thank you so much, sir. Thank you for
Thank
the
you.
very insightful sessions. And I hope it is very much engaging for the participants also. Thank you so much for your time and the effort which you have put up in delivering this session, sir.
Thank you.
I really appreciate it, sir. Thank you so much. So to the participants, tomorrow we will be meeting at 6 p.m. We will be having the two sessions. One is by Professor V.V. Rao from 6 to 7:30 p.m. on the vacuum chambers and system design. And the another session from 7:30 to 9 p.m. By Professor Muhammad Javed Sidki. Right? It is on the vacuum technology in IC fabrication. So I request everyone to join tomorrow at 6 p.m. And please fill the feedback forms for the session 3 and 4. So they are circulated in the chat box also. They are added in the WhatsApp group. So everybody is requested to fill the feedback form. And thank you so much, sir. Thank you
Thank you.
for
Thank you,
taking
madam.
out the time.
Thank you. Thank you.
Yeah. So we can end the meeting right now.
What?
Huh?
Thank you. Thank you.
Okay. Thank you. So I hope everybody has taken the links. So we are ending the meeting.
Hello. Yeah, tell me. Hello.